The Hubble Space Telescope marked one of the greatest scientific revolutions of the 20th century and the beginning of the 21st century. Since its launch, in April of the year 1990, Hubble has been responsible for revealing images of the universe never seen before, allowing the observation of distant galaxies, nebulae, star clusters, and planets of our own solar system with a precision never before achieved. Its main mirror, with 2.4 meters in diameter, and its instruments sensitive to visible light, ultraviolet, and part of the near-infrared, opened an unprecedented window for modern astronomy. However, despite its gigantic impact, Hubble has always carried physical and technological limitations. The main one was precisely the range of light it was able to capture. It was not capable of penetrating deeply into the infrared, which prevented it from seeing the primordial universe, where the light of the first stars and galaxies was stretched by cosmic expansion. Astronomy had known for decades that to understand cosmic origins, it would be necessary to observe in the infrared. The reason is simple. The universe is in constant expansion, and the farther the object is, the more its light is stretched. This phenomenon is known as redshift, and it makes galaxies formed hundreds of millions of years after the Big Bang detectable only in infrared wavelengths. Hubble, with its architecture mainly focused on visible light, was limited in this aspect. It could capture echoes of the young universe, but it could not pierce through the barrier of cosmic dust and extreme distances with clarity. This created a scientific gap. We knew that the first stars and galaxies existed, but we could not observe them directly. It was from this necessity that the idea of the James Webb Space Telescope was born. Unlike Hubble, which orbits Earth at about 540 kilometers in altitude, James Webb was designed to operate at a distance of approximately 1,500,000 kilometers at the gravitational equilibrium point known as Lagrange point 2. This strategic position keeps it stable, protected from the light of Earth and the Sun by a gigantic thermal shield. This shield, the size of a tennis court, is made of 5 layers that block heat and radiation, ensuring that the scientific instruments remain at extremely low cryogenic temperatures, close to negative 230 degrees Celsius. Only under these conditions is it possible to accurately observe the infrared light emitted by celestial objects that are extremely distant. Another fundamental difference is in the size and design of the mirror. While Hubble has a single mirror of 2.4 meters, James Webb has 18 hexagonal segments coated with gold, which together form a primary mirror with 6.5 meters in diameter. This means that Webb's light-collecting area is more than 6 times greater than Hubble's. In simple terms, it is capable of capturing many more photons, which translates into sharper images and much more detailed data. This ability to capture fainter light is essential to see objects that formed in the very first millions of years after the birth of the universe. Beyond the difference in optical technology, the scientific goals also evolved. Hubble was essential to measure the Hubble constant, refine the age of the universe, observe distant supernovae, and confirm the existence of dark energy. It also revolutionized the study of stellar evolution, planetary atmospheres, and galaxy formation. James Webb, on the other hand, was conceived with 4 main objectives: to investigate the light from the first stars and galaxies that emerged after the Big Bang, to study the formation and evolution of galaxies over time, to analyze the formation of stars and planetary systems, and to examine the atmospheres of exoplanets in search of possible conditions for life. In other words, Webb was created to answer questions that Hubble raised but could not resolve. The transition between the 2 telescopes should not be seen as a replacement but as an evolution. Hubble is still in operation, though with limited instruments and natural wear after more than 30 years in orbit. It continues to provide complementary data, especially in the visible light range, while James Webb expands the vision into the deep infrared. Together, they form an unprecedented partnership in the history of astronomy, where one telescope sees the present and the other reveals the distant past of the cosmos. This collaboration marks a new paradigm. It is not only about seeing farther, but about seeing more deeply and understanding cosmic structures that until then were invisible. In the end, Hubble opened the door and showed that it was possible to rewrite astronomy books with deep space images. James Webb, in turn, is the key that allows us to cross that door and dive into the first chapters of the history of the universe. This transition, marked by different technologies, locations, and light ranges, symbolizes a passage of generations in astronomy, from a universe already formed to a universe in formation, where stars, galaxies, and black holes were still taking their first cosmic steps. The James Webb Space Telescope represents the synthesis of more than 2 decades of cutting-edge engineering, where every technological detail was designed to serve a single purpose: to observe the universe in its most primitive state. The difference compared to any other telescope ever built lies precisely in the combination of its segmented mirror, the ability to capture light in the deep infrared, and the sophistication of its scientific instruments. This architecture was not conceived only to see farther, but to overcome physical barriers imposed by cosmic expansion, interstellar dust, and the limits of classical optics. Webb is, at the same time, a masterpiece of space engineering and a machine built to answer questions that once seemed unreachable. The primary mirror is the most iconic and recognizable part of James Webb, composed of 18 hexagonal segments of beryllium, each measuring about 1.5 meters in diameter. This assembly forms a circular structure 6.5 meters in diameter. Beryllium was chosen for its resistance, lightness, and thermal stability at extremely low temperatures, conditions under which the telescope must operate to capture infrared light. The surface of the segments received an ultra-thin gold coating, approximately 100 nanometers thick. This gold is essential because it efficiently reflects infrared radiation, allowing each collected photon to be directed to the instruments with minimal energy loss. In total, Webb's light-collecting area is more than 6 times larger than that of Hubble, which makes it sensitive to weaker signals coming from very distant galaxies. The segmented structure was not only an aesthetic choice, but also a logistical necessity. A monolithic mirror 6.5 meters in diameter could never have been launched aboard a rocket with current technology. The solution was to create a foldable mirror capable of compacting for the trip and then unfolding in space with millimetric precision. This operation involved more than 300 potential points of failure identified by the team, each of which had to work perfectly for the telescope to succeed. When it finally unfolded in space in January of the year 2022, each segment had to be individually adjusted by actuators until they all worked together as a single uniform mirror. This calibration process took months, and when the first images arrived, they proved that the daring design had been an absolute triumph of engineering. For this mirror to work correctly, the telescope must operate in conditions of extreme cold. This is why James Webb was equipped with a gigantic sun shield made of 5 layers of Kapton composite material, each layer thinner than a human hair. This shield, approximately the size of a tennis court, is able to block solar radiation and keep the instruments on the shaded side of the telescope at temperatures close to negative 230 degrees Celsius. This thermal protection is vital because any heat could generate unwanted infrared radiation, contaminating the observations. The temperature control is so precise that the side illuminated by the sun can exceed more than 100 degrees Celsius, while the scientific side remains at cryogenic temperatures. This radical contrast is only possible thanks to the multi-layer design, where each Kapton film reflects and dissipates heat in sequence. At the heart of James Webb are 4 main instruments, which together cover the spectrum from near-infrared to mid-infrared. NIRCam, or near-infrared camera, is the instrument responsible for capturing detailed images of the cosmos and also for aligning the mirror segments. NIR-SPEC, or near-infrared spectrograph, allows the study of the light from objects and breaks it down into its wavelengths, revealing the chemical composition, temperature, and velocity of distant galaxies. MIRI, or mid-infrared instrument, is capable of seeing through cosmic dust and observing regions of star formation that would be invisible to optical telescopes. Finally, the FGS NIRIS, the fine guidance sensor and slitless spectrograph, helps with the telescope's pointing control and also offers unique capabilities for the observation of exoplanets and multiple systems. These instruments are cooled to extremely low temperatures, especially MIRI, which requires an active cryogenic system to operate around negative 266 degrees Celsius. Each of these technologies was designed to work in harmony, forming a true scientific symphony. The mirror collects the light, the thermal shield ensures the purity of the observation, and the instruments decipher the message hidden in photons that traveled billions of years to reach the telescope. This orchestration is what allows Webb to reveal phenomena such as galaxies formed when the universe was less than 500 million years old, colossal black holes in early stages, and cosmic structures that challenge the very standard model of cosmology. The precision achieved is so great that the telescope is capable of detecting tiny variations of light in distant stars caused by exoplanets in transit, thus identifying molecules in the atmospheres of worlds that orbit other stars. Webb is not merely a technological extension of Hubble, it is a qualitative and conceptual leap. Where Hubble provided colorful and inspiring images, James Webb delivers data that redraw equations, graphs, and theories. This difference reflects the maturity of science itself. We no longer seek only visual wonder, but answers to the oldest mysteries, such as the origin of the first cosmic structures and the nature of invisible matter. With its segmented mirror, its sensitivity to the deep infrared, and its instruments calibrated at the limit of precision, James Webb has become the most powerful tool ever built to decipher the secrets of the universe. The James Webb Space Telescope is not just another observatory in orbit. It is a true cosmic time machine. Its main feature, which sets it apart from all previous instruments, is the ability to observe infrared radiation coming from the far reaches of the universe. This radiation is the very light emitted by stars and galaxies in the first millions of years after the Big Bang, but which, after crossing billions of light years of cosmic expansion, has been stretched to wavelengths that only the infrared can reveal. That is precisely why Webb has opened a new window. It not only sees far, it sees back in time to moments when the first cosmic structures were emerging. To understand this transformation, it is necessary to revisit the concept of redshift. As the universe expands, the light emitted by distant galaxies is stretched. If a galaxy emitted visible light at the moment of its formation, that same light, after traveling 13 billion light years to reach our telescopes, arrives stretched into the infrared. Optical telescopes like Hubble are unable to capture this transformed radiation. Webb, on the other hand, was designed specifically to operate between the near-infrared and the mid-infrared, covering wavelengths that reveal these ancestral signals. This is equivalent to swapping ordinary glasses for special lenses that allow us to see the invisible and, with that, to penetrate eras of the cosmos that until then were only theory. Another factor that makes Webb revolutionary is its ability to pass through clouds of cosmic dust. Visible light is easily blocked by dust particles that permeate regions of star formation, hiding the nurseries of stars and planets. However, infrared light crosses these barriers almost without being affected. This means that Webb can reveal hidden processes of starbirth, growing galaxies, and even planetary systems in their early stages. This aspect is fundamental to understanding not only how the universe was formed, but also how worlds similar to ours may have arisen throughout cosmic history. In addition, the combination of extreme sensitivity and high angular resolution allows Webb to identify objects that simply would not be detected otherwise. Galaxies so faint that they were invisible to Hubble appear clearly in Webb's images. Supermassive black holes that formed too early in the universe begin to be tracked. Structures of gas and dust display patterns that challenge models of cosmic evolution. This capability is not just an incremental improvement, it is a paradigm shift. Where once we saw a universe already relatively mature, we now begin to see its turbulent childhood. Another essential point is the spectroscopic precision of James Webb. It is not enough to observe a distant galaxy as a luminous point. It is necessary to break down its light and extract information about its chemical composition, temperature, density, and recession velocity. Webb's spectroscopic instruments do this with unprecedented detail. This is how we know that some of the observed galaxies possess gigantic masses when the universe was only a few hundreds of millions of years old, something that challenges traditional formation models. It is also how we detect the presence of complex molecules in the atmospheres of exoplanets tens or hundreds of light years away. This spectral depth is what allows the transformation of beautiful images into robust science. By opening this new window, Webb brought with it inevitable tensions with the standard cosmological model. Observations of very massive galaxies in early epochs, of black holes formed too soon, and of structures that appear more mature than they should be at that stage, have sparked intense debates in the scientific community. Some astronomers argue that it is just a matter of refining models and that the data will fit with adjustments. Others believe it may be the beginning of a profound revision of how we understand the formation of the first cosmic structures. This uncertainty is precisely what makes Webb so fascinating. It not only answers questions, it creates new and perhaps more complex ones. In summary, James Webb changed our window onto the young universe because it made visible what was previously invisible. It allows us to see not only galaxies in formation, but also the processes that shape the cosmos from its earliest instance. Where before we had only hypotheses based on models and simulations, we now have concrete data, images and spectra that transport us to the universe's childhood. This change in perspective is not only scientific, it is also philosophical. To look at the first instance of the cosmos is, in a certain sense, to look at our own origins, since all the matter that composes us began in those primordial processes. The understanding of how gravity acts on light was one of the greatest scientific revolutions of the 20th century, a direct result of Albert Einstein's general theory of relativity. Before it, gravity had been understood, since Isaac Newton, as an invisible force acting at a distance, pulling massive bodies toward one another. But in the year 1915, Einstein presented a radically different vision. Gravity was not a force, but rather the curvature of space-time caused by the presence of mass and energy. In other words, stars, planets, and galaxies do not merely occupy space. They shape the very fabric of the universe, creating invisible valleys and depressions through which light and matter are forced to move. One of the most fascinating aspects of this theory is the effect of gravity on light. If space-time is curved by the presence of mass, then the trajectory of light must also be deflected when it passes near large concentrations of matter. This means that light does not travel in an absolute straight line, but rather in curved paths determined by the geometry of space-time. Einstein described this phenomenon mathematically and predicted that it would be possible to observe the deflection of light from distant stars when it passed close to the Sun or other colossal masses in the universe. This idea seemed counterintuitive at the time, but it was confirmed in the year 1919 during a solar eclipse observed by Arthur Eddington and his team, when the light of stars close to the solar disk was seen shifted in relation to its apparent position in the sky. It was the empirical proof that the theory needed. From this principle came the concept of gravitational lensing. Imagine a massive galaxy or a cluster of galaxies between us and an even more distant object. The enormous mass of this system acts like a cosmic lens, bending the light that passes through it and amplifying its image. In some cases, this generates arcs of light, multiple images of the same object, or spectacular distortions known as Einstein rings. This phenomenon not only confirms Einstein's theory, but also became a powerful tool for modern astronomy. Thanks to gravitational lenses, we can observe objects much more distant and faint than would otherwise be possible with the capabilities of telescopes alone. Gravity, which once seemed to be an obstacle, has become an ally, a true natural telescope sculpted by the universe. The concept of gravitational lensing is also essential for the study of dark matter. This mysterious form of matter does not emit light, nor does it absorb or reflect electromagnetic radiation, but it exerts gravity. When a cluster of galaxies acts as a lens, astronomers can measure the amount of distortion caused in the light of background objects, and with this, infer the presence of invisible matter. This method has already demonstrated that most of the mass of the universe is not made of stars, planets, or gas, but rather of something invisible that we call dark matter. In this way, gravitational lensing is not merely a curiosity predicted by general relativity. It is a practical tool that today helps us map the invisible. There are different categories of gravitational lenses. Strong lenses are those in which the distortion of light is so intense that it results in well-defined multiple images, arcs or complete rings. Weak lenses are more subtle distortions, detectable only through statistical analyses of large samples of galaxies. There are also microlenses, caused by smaller objects such as stars or even planets, which temporarily amplify the light of distant stars as they pass in front of them. Each of these manifestations has different applications, from the search for extrasolar planets to the investigation of the large-scale structure of the universe. Einstein, curiously, believed that we would never see this effect directly outside of rare events such as solar eclipses. For him, the required precision was impossible to achieve in practice. But 21st century astronomy proved otherwise. Not only do we observe gravitational lenses, we use them as everyday tools to probe the cosmos. The Hubble Space Telescope had already shown us spectacular images of arcs and rings formed by gravitational lenses, but it was James Webb that took this technique to a new level. Its sensitivity and reach in the infrared allowed it to detect not only the lensing effect, but also details previously invisible of the magnified objects, revealing extremely young galaxies that would otherwise be unreachable. Therefore, revisiting the concept of gravitational lensing is essential to understanding the importance of James Webb. Without this phenomenon predicted by general relativity, we would be blind to a significant part of the distant universe. With it, we are able not only to confirm Einstein's theory, but also to transform the cosmos into an immense laboratory of physics and cosmology, where the gravity of the most massive structures acts as a magnifying glass, revealing the invisible and multiplying our observational capacity. And it is precisely within this context that one of the most fascinating phenomena ever observed by James Webb arises, the so-called Einstein's cross, an emblematic example of how theory materializes before our cosmic eyes. Among all the examples of gravitational lenses that astronomy has already catalogued, one of the most intriguing is the so-called Einstein's cross. This phenomenon receives its name because, when observed from Earth, it appears as four bright points arranged in the shape of a cross around a closer central galaxy. In reality, it is not four different objects, but the same distant light source being distorted and multiplied by the gravity of the intermediate galaxy. It is as if gravity had built a cosmic kaleidoscope, replicating the image of the same object in multiple directions. James Webb, with its unmatched precision, managed to observe a new case of this phenomenon, providing details that until then were unattainable. The formation of an Einstein's cross is a direct result of general relativity in action. When the light of an extremely distant galaxy or quasar passes near a massive galaxy between us and the original source, space-time curves so intensely that the path of the light is bent into several different routes. These routes, upon reaching us, create multiple images of the same source, seen in distinct positions in the sky. The result is the characteristic cross-shaped figure. In the past, Hubble had already recorded Einstein's crosses, but limited resolution and the inability to penetrate deeply into the infrared restricted the level of detail achieved. James Webb, in turn, not only confirmed the presence of these multiple images, but also managed to analyze the light spectrum of each of them, revealing scientific data of inestimable value. In the specific case recently observed by James Webb, the analysis of the distortion showed something even more impressive. For that Einstein's cross to form in the recorded way, the presence of a colossal amount of invisible matter around the lensing galaxy would be necessary. This excess of gravity could only be explained by a gigantic halo of dark matter surrounding the intermediate galaxy. In other words, the Einstein's cross not only once again confirmed the general theory of relativity, but also offered direct evidence of the distribution of dark matter on cosmic scales. This is the kind of data that places James Webb at the forefront of cosmological discoveries. By observing distortions of light, it reveals not only what is emitting photons, but also that which remains invisible. Another important aspect of the Einstein's cross observed by Webb is the amplification of the distant source. The gravitational lens acts as a natural telescope, making visible details that would be impossible to detect otherwise. In the case in question, the galaxy or quasar behind the lensing galaxy became accessible at levels of detail that allow the investigation of its chemical composition, its approximate age, and even estimates of stellar mass. This natural amplification, combined with the sensitivity of James Webb, creates a unique partnership. Human engineering adds to the engineering of the universe itself. Gravity, in this sense, ceases to be just a force or a curvature, and becomes a scientific tool capable of multiplying our vision. The symbolism of the Einstein's cross is also relevant. The idea of four images forming a cross around a central galaxy arouses fascination not only among scientists, but also among the general public. This cosmic aesthetic reinforces the almost artistic character of the universe, as if gravity were painting geometric patterns with light. But beyond beauty, there is hard science. Each of these images is a fragment of information that, when analyzed together, provides measurements of distance, mass, composition, and even the velocity of expansion of the universe on deep scales. Webb, by breaking down this light, transforms this visual spectacle into concrete data that help refine or question the standard cosmological model. Finally, the observation of the Einstein's cross by James Webb has implications that go far beyond the event itself. It confirms that gigantic halos of dark matter play a crucial role in the formation and evolution of galaxies. It reinforces the precision of general relativity in predicting extreme phenomena. And above all, it paves the way for new surveys of gravitational lenses in different regions of the sky, which may reveal even more crosses, arcs, and rings. Each of these cases is, at the same time, a confirmation of cosmic laws and a window to new mysteries. By recording this cross, Webb not only validated century-old predictions, but added yet another piece to the puzzle of the invisible matter that dominates the universe. The observation of the Einstein's cross by the James Webb Space Telescope brought an impressive confirmation. The geometry of the cross and the degree of amplification of the background source could only be explained by the presence of a colossal amount of invisible matter surrounding the lensing galaxy. This excess of gravity is far greater than what could be produced solely by the observable stars and gas. The inevitable conclusion is that the galaxy is immersed in a gigantic halo of dark matter, an invisible structure that, although we cannot see it, exerts enough gravitational force to shape space-time and create the recorded distortions. Dark matter halos are predicted by the standard cosmological model as invisible structures that envelop galaxies, functioning as gravitational scaffolds. Without them, it would be impossible to explain the rotational stability of galaxies, since the amount of visible matter would not be sufficient to keep the stars in orbit without them escaping. Furthermore, the early formation of cosmic structures depends on these halos. They attract baryonic matter, the common type of matter formed by protons, neutrons, and electrons, and serve as gravitational seeds from which galaxies form. However, the direct detection of these halos is impossible because dark matter does not interact with light. The only way to confirm them is to observe indirect gravitational effects, such as the bending of light in gravitational lenses. That is precisely what the Einstein's cross provided. The spectroscopic analysis performed by Webb showed that the distortion of the background light required a gravitational field much more intense than that generated by the visible mass of the intermediate galaxy. Estimates suggest that most of the mass involved, more than 80%, was in the form of invisible matter. This halo has no defined edges, but extends far beyond the region occupied by visible stars, forming a sphere of gravitational influence that can reach hundreds of thousands of light-years in diameter. It is as if galaxies were just small, luminous islands floating in invisible oceans of dark matter. By recording the Einstein's cross, Webb provided further concrete evidence of the existence and importance of these invisible oceans. This result also has direct implications for models of dark matter distribution in the universe. Different theories attempt to explain how this mysterious substance behaves on cosmic scales. Some models suggest that it organizes itself into smooth structures, while others argue that it forms dense clumps. The detailed observation of the Einstein's cross helps to constrain these hypotheses, showing that the distribution must be sufficiently dense to generate multiple images and, at the same time, sufficiently stable to maintain the symmetry of the cross. This is fundamental because the more observations of this kind we have, the more precise the invisible maps of the cosmos will become. Another important aspect is the connection between dark matter halos and the early formation of massive galaxies. Webb has revealed objects much larger and older than expected for the first billions of years of the universe. The presence of gigantic halos of dark matter may help explain this enigma, since their extra gravity would provide the necessary conditions for ordinary matter to clump together quickly, forming large galaxies in very short times. This could be a key to resolving some of the tensions that the new data are creating with the standard cosmological model. Finally, the Einstein's cross observed by Webb is not just a geometric curiosity or a triumph of general relativity. It is, above all, a practical demonstration of the central role of dark matter in the universe. This invisible halo is what sustains the cross, what amplifies the light, and what makes visible a source that would otherwise remain hidden. Each observation of this kind is a window to the invisible, a proof that most of the universe is not composed of bright stars, but of matter that does not emit light and only reveals itself when it distorts the very geometry of space-time. Webb, in this sense, not only photographs the cosmos, it maps its shadows, revealing the invisible fabric that sustains everything that exists. The observation of a giant halo of dark matter behind the formation of the Einstein's cross, recorded by the James Webb Space Telescope, is not just a specific proof of the existence of this mysterious substance. It is, above all, a window to understanding how invisible matter is distributed throughout the universe on a large scale. Since the first evidence of dark matter emerged in the second half of the 20th century, with the measurements of galaxy rotation made by Vera Rubin, scientists have known that there is far more mass in the cosmos than we can directly see. However, knowing that it exists is only the first step. The fundamental question is how it organizes itself and what role it plays in cosmic architecture. The data collected by Webb suggest that dark matter is not spread randomly, but rather structured into halos that surround galaxies and galactic clusters. These halos function like invisible gravitational spheres, sustaining the galaxies within them. The detection of the Einstein's cross is direct proof that the distribution of dark matter is sufficiently dense and uniform in large regions, to the point of creating symmetrical and clear distortions in the light coming from background objects. This type of observation reinforces the idea that dark matter is responsible for maintaining cosmic cohesion, and that without it, the universe would have a completely different appearance. Based on these results, we can imagine the universe as an immense invisible web, known by cosmologists as the cosmic web of dark matter. This structure connects galaxies through filaments that stretch across millions of light-years. The regions of greatest concentration of dark matter form nodes where entire galaxies are drawn and held. Without this invisible web, galaxies would not have grouped into clusters, and the universe would be more rarefied, with isolated stars instead of grand structures. Webb, by observing gravitational distortions, such as the Einstein's cross, helps map these filaments, even if indirectly, confirming that the cosmos is sustained by an invisible framework. An important point revealed by these data is the scale of the reach of dark matter. While visible light only shows the luminous parts of galaxies, their disks, spiral arms, and star-forming regions, gravitational lenses reveal that the invisible halos extend far beyond this, with diameters reaching hundreds of thousands of light-years. This means that most of a galaxy's mass lies outside what we can see, spread across an invisible sphere that dominates its gravity. Webb, by precisely capturing the degree of distortion of the Einstein's cross, allowed the calculation of the size of this halo, reinforcing estimates that about 85% of the matter in the universe is composed of dark matter. Another relevant aspect is the symmetry of the distortions. If dark matter were distributed irregularly, with large gaps or holes in its density, the pattern of gravitational lenses would be asymmetrical or chaotic. However, the regularity observed suggests that the distribution is relatively smooth on large scales, even though it may contain smaller clumps on reduced scales. This information is essential for refining cosmological models and may even help to rule out some alternative hypotheses, such as modified gravity theories, that try to explain the effects without invoking dark matter. Ultimately, the Einstein's cross observed by James Webb does not merely show us a beautiful image of the cosmos, but a map of the invisible. It confirms that dark matter is distributed in a way consistent with halo models and reinforces the idea of a cosmic web sustaining the universe. Each cross, each arc, or each ring recorded by Webb is a piece of this puzzle, which may one day allow us to understand not only where dark matter is, but also what its true nature is. Until that happens, these observations offer us the best available cartography of the invisible, a map traced by light that traveled billions of years only to be distorted along the way, and in doing so, reveal what our eyes could never see directly. One of the most impactful discoveries of the James Webb Space Telescope was the identification of surprisingly large galaxies at a time when, according to traditional models, they should not yet exist. These galaxies, observed when the universe was only between 300 and 600 million years old, appeared in Webb's images as extremely red points. This tone is not due to their intrinsic color, but to the fact that the light from these structures was stretched by redshift, the result of cosmic expansion over more than 13 billion years of travel. When analyzed in detail, astronomers realized that these were objects far too massive and mature for the epoch at which they were being observed. According to the standard cosmological model, the early universe should have been composed almost entirely of clouds of hydrogen and helium gas, still in the process of cooling and condensing. The first stars would have begun to form a few 100 million years after the Big Bang, and only gradually should these stars have clustered into small galaxies. The growth of these galaxies into larger structures should have taken billions of years. However, James Webb revealed galaxies already with billions of solar masses at an extremely early period. This is equivalent to finding a gigantic city in the middle of a newly formed desert, when we expected only small villages. These red dots immediately generated a wave of debate in the scientific community. Some astronomers interpreted the data as evidence that galaxy formation models need to be adjusted. Others went so far as to suggest that we are facing a possible sign of new physics, something that could challenge even the standard cosmological model known as lambda CDM. One of the most intriguing hypotheses is that some of these structures are not galaxies in the classical sense, but rather conglomerates formed around primordial black holes, capable of accelerating star formation on a much faster scale than predicted. The massive galaxies detected by Webb also showed signs of heavy elements such as oxygen and carbon, something that indicates that previous generations of stars had already lived and died in supernova explosions, enriching the interstellar medium. But how could so many generations of stars have formed, evolved, and exploded in such a short interval? This is one of the greatest current tensions between Webb's data and existing theories. It is as if the timeline of cosmic evolution had been compressed, requiring processes that we thought took billions of years to occur in just hundreds of millions of years. To try to resolve this enigma, scientists are using sophisticated computer simulations, inserting new variables that could accelerate the growth of these structures. One possibility is that the density of dark matter in the early universe was even greater than we imagine, providing enough gravity to rapidly cluster large amounts of gas. Another is that the first black holes played a more active role than we had assumed, functioning as catalysts for the formation of galaxies around them. There is also the chance that part of these observations may be misinterpreted, and that some of these galaxies are actually closer objects confused because of the intensity of the redshift. But so far, all analyses converge on the fact that we are indeed facing massive structures in an extremely young universe. These red dots, therefore, are not just bright spots in infrared images. They represent a direct challenge to our understanding of cosmic history. They force us to reconsider how the first stars were born, how galaxies grew, and even whether the physical laws we know are sufficient to explain the first moments of the universe. It is possible that in the future, new observations and analyses will integrate these objects into already existing models, adjusting timelines and mechanisms. But it is also possible that we are facing a rare opportunity, the chance to profoundly reshape our understanding of the birth of the cosmos. Faced with the surprise of finding extremely massive galaxies in the young universe, only a few 100 million years after the Big Bang, scientists began to seek hypotheses that could account for this apparent cosmic anticipation. One of the boldest ideas that emerged from the James Webb Space Telescope data is the existence of so-called black hole stars. Unlike conventional stars, which are born from the nuclear fusion of hydrogen and are sustained by the balance between gravity and thermal pressure, these hypothetical stars would have as their internal engine a black hole at the center, providing energy through completely different processes. The proposal is that in the primordial universe, regions of extremely high density could have collapsed rapidly to form black holes. These black holes, instead of remaining isolated as compact objects, could have become enshrouded in dense clouds of gas. The intense gravitational field would attract large amounts of matter, and as it fell toward the black hole, this matter would be heated to extreme temperatures, releasing enough radiation to illuminate the structure like a star. Thus, instead of depending exclusively on nuclear fusion to shine, These hybrid stars would be powered by a gravitational engine in their core, sustaining luminosity and growth on a much faster scale. This hypothesis is attractive because it solves two problems at once. First, it explains how such luminous and massive structures could have appeared so early. With a central black hole devouring matter at a frenzied pace, the growth of these protostructures would have been much faster. Second, it offers an alternative to interpret the red dots observed by James Webb. Instead of being only ordinary galaxies that challenge traditional models, some of them could be a new type of cosmic object, never before confirmed, but theoretically predicted. The black hole stars would therefore be living fossils of an era when the rules of stellar formation were different from those we know today. The functioning of these hypothetical stars also raises fascinating questions. Unlike conventional stars, which go through well-defined cycles of life and death, black hole stars could have a more chaotic evolution. The rapid growth of the central black hole would tend to swallow much of the available material, while at the same time, the emitted radiation would push part of the gas outward. This unstable balance could result in periods of extreme luminosity, followed by dimming, creating patterns of variability different from those we know in normal stars. Webb, by recording the brightness and spectra of these red dots, may help identify whether we are truly facing such objects. There are also implications for large-scale cosmology. If black hole stars really existed, this would mean that the first supermassive black holes, those we see today at the centers of large galaxies, could have formed much more quickly than we previously thought. Instead of taking billions of years to grow from small seeds, they could have emerged already on a large scale, fueled by these hybrid stellar phases. This would help explain why James Webb has already detected black holes with masses of millions or even billions of suns in very early epochs of the universe, something that the classical model of slow growth through gas accretion cannot fully justify. Of course, so far the black hole star hypothesis remains speculative. There is no definitive observational confirmation that these objects really exist, but the beauty of science lies precisely in this. When the data challenge existing models, bold theories emerge to try to address the enigma. James Webb, by opening this new window onto the young universe, may be the key to confirming or discarding this idea in the coming years. If proven, black hole stars would be one of the most revolutionary discoveries in modern astrophysics, showing that the cosmos once experienced forms of luminosity and structure that no longer exist in the present day. The discovery of galaxies that are far too massive and luminous for such an early stage of the universe, along with the possibility of the existence of black hole stars, represents a direct challenge to the chronology established by modern cosmology. According to the standard model known as lambda CDM, the sequence of cosmic formation is relatively well defined. In the first 380,000 years after the Big Bang, the cosmic microwave background radiation was released, marking the period when the universe became transparent to light. In the following 100 to 200 million years, the first stars should have begun to form, composed almost exclusively of hydrogen and helium. Only hundreds of millions of years later would small galaxies gather into larger groups, slowly evolving until generating massive structures. However, what James Webb is showing seems to skip several steps in this timeline. Instead of finding sparse, incipient small galaxies, it reveals galaxies already large, with masses of billions of suns and evidence of successive generations of stars that enrich their environment with heavy elements. This suggests that, in just a few 100 million years, processes we expected to take billions had already taken place. It is like watching a movie and realizing that the first chapters were condensed into minutes, leaving gaps between what should have happened and what we are actually observing. This discrepancy challenges not only the chronology, but also the fundamental mechanisms of cosmic formation. The most accepted simulations indicate that star formation should be gradual, limited by the amount of available gas, the efficiency of nuclear fusion, and the dynamics of dark matter. However, the red dots suggest a formation at an accelerated, almost explosive pace. The hypothesis of black hole stars tries to fill this gap by proposing alternative engines of luminosity and growth, but even this idea still needs to be tested against more robust observational data. Another critical aspect is the role of cosmic reionization. It is believed that between 400 and 800 million years after the Big Bang, The ultraviolet radiation emitted by the first stars and galaxies reionized the universe's neutral hydrogen, making space once again transparent to light on a large scale. The problem is that the presence of galaxies so large and luminous before this period suggests that reionization may have occurred much more quickly and intensely than predicted. This would require rewriting the chronology not only of galaxy formation, but of the very evolution of the intergalactic medium. There is also an important implication for the growth of supermassive black holes. The fact that James Webb detects black holes with masses of millions or billions of suns so early in the universe contradicts classical models of slow growth by accretion. If these giants already existed at such early stages, it is likely that they formed by mechanisms not yet fully understood, such as direct collapses of gas clouds, or even the contribution of black hole stars. This calls into question the notion that black holes are merely the final product of stellar evolution, suggesting that they may have played a leading role since the very beginning. Finally, this challenge to cosmic chronology creates inevitable tension with the standard cosmological model. The lambda CDM framework is extremely successful in explaining a series of observations, from the cosmic microwave background to the large-scale distribution of galaxies. But at the same time, Webb's discoveries seem to indicate that there are significant gaps to be filled. The solution may lie in refined adjustments of parameters, such as the density of dark matter or the efficiency of star formation. But it is also possible that we are facing the need to expand our understanding, incorporating new physics not yet discovered. In summary, the red dots and the associated hypotheses are not just astronomical curiosities. They are reminders that the universe may not follow the timelines we establish from our theories, and this, for science, is a gift. Each challenge to the standard chronology is also an opportunity to move forward and perhaps rewrite part of cosmic history. Galaxies have always been understood as complex structures whose formation depends on a delicate balance between gravity, interstellar gas, supernova explosions, stellar radiation, and the influence of dark matter. For decades, astrophysicists have built computer simulations based on these processes, capable of reproducing with relative accuracy the distribution of galaxies we see today. However, recent data from the James Webb Space Telescope have begun to reveal uncomfortable contradictions with these simulations, especially when it comes to the universe's first few 100 million years. The central problem is the speed of growth. According to traditional models, the first stars, called Population 3, were formed almost exclusively of hydrogen and helium and should have appeared in small clusters. These stars, upon exploding as supernovae, would enrich the medium with heavy elements, allowing new generations of stars to form in more complex environments. This cycle should have taken hundreds of millions or even billions of years to create large galaxies rich in chemical elements. But what Webb is showing are galaxies that already appear chemically mature and with extremely high stellar masses, at a time when, according to the models, only incipient structures should exist. The most advanced cosmological simulations, such as those using supercomputers to track the evolution of billions of dark matter and gas particles, cannot reproduce the number of massive galaxies observed so early. This raises two possibilities. Either there are physical processes that have not been properly included in these simulations, or there is some fundamental aspect of the physics of the universe that we still do not understand. It is possible, for example, that the efficiency of star formation in the earliest times was much higher than we supposed, or that alternative mechanisms, such as primordial black holes, accelerated the accumulation of mass. Another point of tension is the luminosity of these galaxies. Some of them are so bright that they defy the limits of energy emission that models attribute to such young systems. This suggests that star formation may have occurred in explosive bursts, rather than through gradual, constant growth. However, such bursts should also generate strong stellar winds and explosions, capable of dispersing gas and hindering the formation of new stars, which contradicts the stability necessary to sustain massive galaxies. This contradiction is one of today's greatest enigmas: how to reconcile extremely high star formation rates with the need to maintain gas reserves to sustain long-term growth. In addition, there are questions about the spatial distribution of these early galaxies. James Webb has shown that they are not isolated, but seem to cluster into protoclusters, connected by filaments reminiscent of the cosmic web on smaller scales. This means that the dark matter network itself may have structured more quickly than models predict. If the cosmic web emerged at such early stages, this implies significant adjustments in the equations that describe the universe's expansion and evolution. These tensions do not mean that the entire theoretical edifice of cosmology is about to collapse. The lambda CDM model remains extremely effective in describing many aspects of the universe on large scales. But the discrepancies exposed by Webb are clear signs that the history of galactic evolution is more complex than we thought. It is possible that the problem lies in the details, such as gas cooling rates, supernova feedback, or the interaction between radiation and dark matter. But it is also possible that the root of the issue lies in deeper fundamentals, such as the nature of dark matter itself or dark energy. Ultimately, the tensions with galactic evolution models revealed by James Webb are a reminder that science is not static. Theories that worked for decades now need to be tested against more detailed and challenging data. This confrontation between prediction and observation is what drives scientific progress. And in the case of Webb, every discrepancy is also an opportunity, the chance to improve our simulations, revise our equations, and perhaps take the first steps toward a new understanding of the cosmos. Among the most impressive images produced by the James Webb Space Telescope is the observation of a set of 5 galaxies in gravitational interaction, a cosmic spectacle that became known as the quintet. This collective plunge, in which the galaxies approach and begin to collide, represents a unique opportunity to study in real time the processes that shape the universe on gigantic scales. The collision of galaxies is not a rare event in astronomical terms, but capturing 5 systems interacting so clearly is something extraordinary. Webb, with its infrared sensitivity and unprecedented resolution, revealed details that were previously invisible. Distorted spiral arms, streams of gas being stripped away, and active nuclei shining intensely at the center of these galaxies. These observations are fundamental because galaxy collisions are engines of cosmic evolution. For billions of years, the universe has been sculpted by encounters, mergers, and gravitational interactions of this kind. Our own galaxy, the Milky Way, bears scars of past mergers and is already on a collision course with the Andromeda Galaxy, an event expected to occur in about 4 billion years. Observing the quintet with Webb is, therefore, like looking into the future of our own galaxy, seeing in other systems what will one day happen to us. But beyond curiosity, these data allow us to investigate how the merging of galaxies influences star birth, the growth of central black holes, and the redistribution of matter in the universe. The quintet observed by Webb also offers valuable clues about the effects of gravity on large scales. When galaxies approach, their gas clouds collide, compress, and trigger bursts of star formation. These bursts, in turn, illuminate vast regions with young stars while releasing radiation and winds that alter the dynamics of the remaining gas. Webb managed to capture these regions in unprecedented detail, showing that collisions not only destroy structures, but also create new cycles of star birth. It is a process of death and rebirth that repeats throughout cosmic history. Another fascinating aspect of the quintet is the presence of active galactic nuclei, fueled by supermassive black holes. During collisions, large amounts of gas and dust are funneled toward the centers of galaxies, serving as fuel for these black holes. The result is explosions of radiation that can outshine the entire surrounding galaxy. Webb, with its infrared vision, is able to pierce through the dust surrounding these nuclei and directly observe the accretion processes. This provides crucial data on how black holes grow amid cosmic interactions and how in turn they influence the evolution of their host galaxies. The observation of this rare plunge of 5 galaxies also reinforces the importance of gravitational interactions in the formation of larger structures. Galaxies do not live in isolation. They are part of groups and clusters that interact constantly. The quintet seen by Webb is a microcosm of this process, a clear example of how gravity acts as an organizing force on gigantic scales. Each distorted arm, each stream of stripped gas, each active nucleus is a clue about how the universe has evolved over billions of years. Without these interactions, the cosmos would be a much more static and monotonous place. It is in the chaos of collisions that the conditions for cosmic innovation and diversity arise. Ultimately, the rare plunge of 5 galaxies captured by James Webb is not just a beautiful astronomical image, but a living document of history in motion. It shows that the universe is dynamic, that its structures are not fixed, and that even entire galaxies are shaped by inevitable encounters. Every detail recorded by Webb in this quintet is a piece of a puzzle that helps us understand not only the universe's past, but also the future of our own galaxy. Collisions and mergers of galaxies are some of the most transformative events in the entire cosmic history. Contrary to what common sense might suggest, these encounters are not rare exceptions, but fundamental processes that have shaped the universe since its first billions of years. The James Webb Space Telescope, by recording in detail the rare quintet of interacting galaxies, has provided an unprecedented view of the complexity of these phenomena, revealing how they not only destroy already established structures, but also create new forms of cosmic organization. On human scales, the collision between galaxies may sound like an absolute catastrophe, but on cosmic scales, the scenario is different. The distances between stars within a galaxy are so vast that even during collisions, the chance of 2 stars colliding directly is practically zero. What really collides are the immense halos of gas, dust, and dark matter that surround these structures. When these components come into contact, they form compression waves that trigger explosive bursts of star formation. It is in this process that we see vast regions dotted with young, bright stars, visible in Webb's images as glowing patches amidst gravitational chaos. These bursts of star formation have profound consequences for the evolution of galaxies. Young, massive, and hot stars emit intense radiation and generate powerful stellar winds that quickly shape the surrounding interstellar medium. Many of them end their lives in supernova explosions, enriching the environment with heavy elements such as oxygen, carbon, iron, and silicon. Thus, each cosmic collision not only creates new stars, but also seeds the universe with the elements necessary for the formation of planets and ultimately for the emergence of life. What at first glance seems like destruction is in reality the engine of continuous renewal. Another fundamental aspect of collisions is the role of supermassive black holes located at the centers of galaxies. When 2 galaxies merge, enormous amounts of gas and dust are funneled toward the core, serving as fuel for these gravitational giants. The process results in active galactic nuclei, which can shine brighter than all the stars in the galaxy combined. Webb, with its privileged infrared vision, has revealed how these nuclei feed at the heart of the galactic quintet, showing that cosmic encounters not only accelerate star formation, but also the growth of central black holes. This feedback cycle is essential to understanding how galaxies and black holes evolve together. In the long term, collisions and mergers lead to the formation of even larger structures. Many galaxies we see today as giant ellipticals were born from the merger of several spirals in the distant past. These mergers erase the delicate spiral structure and create more chaotic, yet massive and stable systems. Moreover, on even larger scales, successive encounters of galaxies contribute to the formation of clusters connected by filaments of the cosmic web of dark matter. Each merger, each interaction, is a brick in this immense universal edifice. The recording of the quintet by James Webb is therefore a unique opportunity to study in detail a process that is common but rarely observed with such clarity. It confirms that the universe is dynamic and that its structures are not immutable, but rather the result of billions of years of encounters and transformations. If today we look at the sky and see galaxies with defined shapes, majestic spirals, or immense ellipticals, it is because in the past they went through similar collisions. And if we project into the future, we know that our own Milky Way in a few billion years will be transformed into an entirely new galaxy when it finally merges with Andromeda. Thus, cosmic collisions should not be seen only as catastrophes, but as moments of creation. They are the great sculptors of the universe, shaping galaxies, nurturing stars, and feeding black holes. Webb, by showing us such a clear and impressive example, reinforces the idea that it is in apparent disorder that we find the key to the greater order of the cosmos. At the heart of most known large galaxies lies a supermassive black hole, with masses ranging from millions to billions of times the mass of the Sun. These gravitational giants exert profound influence on the fate of their host galaxies. One of the most intriguing questions of modern astrophysics is to understand how these black holes manage to grow so much in such a short time, especially in the young universe. The James Webb Space Telescope has brought new clues, revealing that galaxy collisions and mergers play a central role in this process of feeding and growth. When two or more galaxies enter into gravitational interaction, the tidal forces generated distort their disks and spiral arms, creating streams of gas and dust that are funneled toward the center. This material, rich in hydrogen and other elements, acts like a cosmic river flowing toward the central black hole. As this matter approaches, it forms an accretion disk in which the gas is compressed and heated to temperatures of millions of degrees. The energy released in this process makes the galaxy's core shine intensely, creating an active galactic nucleus. In some cases, the radiation is so powerful that it outshines all the stars in the galaxy combined. This feeding process does not occur smoothly, but in dramatic bursts. During a collision, the sudden inflow of gas into the center can trigger phases of accelerated black hole growth. Webb, by observing the quintet of interacting galaxies, clearly showed regions where infrared light penetrates the dust and reveals hidden active nuclei. These data confirm that galaxy mergers are not merely aesthetic events in the cosmos, but efficient mechanisms for the growth of supermassive black holes. It is through these encounters that the giants of the universe receive much of their fuel. The impact of collisions is not limited to growth. The energy released by black holes in their feeding phases returns to the surrounding environment in the form of powerful jets and winds, a phenomenon known as feedback. This feedback can both stimulate and inhibit the formation of new stars. In some cases, the energy heats the interstellar gas, preventing it from collapsing to form stars. In others, it compresses clouds of gas and triggers bursts of star birth. This feedback cycle demonstrates the intimate and symbiotic relationship between central black holes and their host galaxies. They grow together, influence each other, and determine one another's evolution. Another aspect revealed by collisions is the possibility of mergers between supermassive black holes. When two galaxies merge, their nuclei may also end up approaching and eventually fusing into an even more massive black hole. This process releases colossal amounts of energy in the form of gravitational waves, distorting the very fabric of space-time. Although these events have not yet been directly detected in the infrared, James Webb provides important clues by showing double or multiple nuclei in merging galaxies, indicating that such encounters are intermediate steps on the path to the final merger of black holes. Webb's observations reinforce an increasingly accepted view. Supermassive black holes are not merely byproducts of stellar evolution, but protagonists of cosmic history. They grow in synchrony with their galaxies, fueled by the flows of matter that collisions provide. Each galactic merger is also a step in the growth of these giants, which over billions of years have reached the colossal proportions we see today. Thus, when we look at the quintet images captured by James Webb, we are not merely witnessing the encounter of 5 galaxies, we are seeing the stage where central black holes are being fed, growing, and preparing to dominate the cosmic stage even more. These events remind us that the history of the universe is not made only of stars and nebulae, but also of invisible and silent forces that dictate the course of cosmic evolution. The images captured by the James Webb Space Telescope of colliding galaxies, such as the rare quintet, are not just records of distant events frozen in space and time. They also function as a kind of cosmic mirror, reflecting the future that awaits our own galaxy, the Milky Way. According to high-precision astronomical measurements, we know that the Milky Way is on a collision course with the Andromeda galaxy. This inevitable encounter is expected to occur in about 4 billion years, an immense span on the human scale, but relatively short in astronomical terms. What Webb reveals in detail in the current collisions of other galaxies is, in essence, what will one day happen here in our cosmic neighborhood. Simulations indicate that when the Milky Way and Andromeda draw near, their spiral shapes will be distorted by tidal forces, creating long arms of stars and gas stretching across space. Many stars will be cast into different orbits, some flung far from the center, others into chaotic trajectories. However, contrary to popular imagination, the stars themselves are highly unlikely to collide directly, given the enormous distances separating them. What will truly collide are the vast clouds of interstellar gas and dust, triggering bursts of star formation similar to those Webb has already recorded in merging systems. Another inevitable outcome will be the encounter between the supermassive black holes at the center of each galaxy. The Milky Way hosts in its core the black hole known as Sagittarius A, with a mass of about 4 million suns, while Andromeda harbors an even larger black hole. When the two galaxies merge, these giants will slowly approach until they eventually collide in one of the most energetic events in the universe, the merger of supermassive black holes, releasing intense gravitational waves capable of rippling through the fabric of space-time in all directions. This type of event is rare and has not yet been directly observed, but future generations of space-based gravitational wave detectors may one day record this distant moment. Webb's observations help us understand the intermediate stages of this process. By studying galaxies currently in full merger, we see how their disks deform, how their cores brighten, and how matter is redistributed on vast scales. This gives us a glimpse of the Milky Way's future. Instead of an elegant spiral with well-defined arms, our galaxy will be transformed into a more chaotic structure and eventually settle into the form of a giant elliptical galaxy. This metamorphosis is not an exception. It is the natural fate of most large galaxies in the universe. Curiously, for the solar system, the collision may be less dramatic than it sounds. Simulations suggest that the Sun and its planets will not be swallowed by any black hole nor destroyed by stellar impacts. What will likely happen is a change of position. The solar system will probably be thrown into a different orbit, perhaps farther from the new galactic center formed by the merger. The night sky, however, will be transformed into an indescribable spectacle, with gigantic arcs of stars and bands of dust illuminating the horizon on scales we can only imagine today. Thus, when Webb shows us quintets of merging galaxies, it is not merely recording distant events. It is offering a preview of what awaits us. These cosmic encounters are an essential part of the universe's evolution, and our own galaxy is no exception. In billions of years, the Milky Way and Andromeda will cease to exist as separate entities and will give rise to a new galaxy, whose shape will be sculpted by the gravitational dance we already witness today in other corners of the cosmos. Among the most surprising discoveries brought by the James Webb Space Telescope are the signs of supermassive black holes already existing in incredibly early epochs of the universe. We are talking about objects with masses of millions or even billions of times the mass of the Sun, found when the cosmos was less than 1 billion years old. This finding deeply challenges our understanding because, according to traditional models, there would not have been enough time for such colossal black holes to form from the collapse of massive stars and gradually grow through gas accretion and smaller mergers. The presence of these giants so early raises a series of questions. How could seeds so small transform into gravitational monsters in just a few 100 million years? Could the first black holes have been born already with much larger masses than stars could produce? Or were there accelerated processes, such as the direct collapse of extremely dense gas clouds, capable of generating black holes with hundreds of thousands of solar masses right at their origin? By observing the universe in its primordial state, Webb has brought clues that point to the need to revisit these hypotheses. Observations indicate that some of these early black holes are located at the centers of already relatively developed galaxies, with intense brightness and signs of nuclear activity. This means that they not only existed, but were in full growth phase, swallowing gas and emitting powerful radiation in the form of active nuclei. The James Webb, with its ability to peer into the deep infrared, managed to see through the dust that hides these nuclei and analyze the spectrum of the emitted light. The results show characteristic lines of ionized elements, clear evidence that supermassive black holes were already shaping their environment in a still adolescent universe. This finding calls into question the classic chronology of cosmic formation. Until recently, it was believed that supermassive black holes were late products, arising after galaxies had grown and matured. Now, the possibility that they were present from the earliest moments suggests that they may have played an active role in the very formation of galaxies. Instead of being just consequences of cosmic evolution, they may have been central agents, accelerating gas condensation, stimulating bursts of star formation, and even defining the structure of the first galaxies. Another fascinating point is that some of these black holes appear to be naked, that is, not surrounded by the large amounts of gas and dust normally expected around a growing object. This makes them even more intriguing, as it contradicts the idea that they should be embedded in dense environments. The existence of naked black holes in the young universe may indicate that different feeding and growth mechanisms were at play, distinct from those we see today in mature galaxies. This diversity of scenarios broadens the mystery even further and demands new theoretical explanations. Ultimately, James Webb's discoveries about black holes in the young universe are not just isolated data. They are milestones that may redefine contemporary astrophysics. By showing that gigantic gravitational wells already existed when the cosmos was still taking its first steps, Webb forces science to reconsider not only how black holes grow, but also what role they played in the very construction of the universe. What once seemed a matter of detail has now become a central question. After all, who was born first, the galaxies or their black holes? When we think of supermassive black holes, the image that usually comes to mind is that of a cosmic object hidden by dense clouds of gas and dust, surrounded by a blazing accretion disk, and in many cases, emitting jets of radiation that stretch across thousands of light years. This is the classical scenario we know from observations of nearby galaxies and active nuclei. However, recent discoveries made by the James Webb Space Telescope in the primordial universe have revealed another face: the existence of apparently naked black holes, meaning those that do not display the typical mantle of matter around them. This distinction is fundamental to understanding the different growth paths of these gravitational giants. Black holes enshrouded in gas follow the traditional accretion model. They are immersed in regions rich in matter, such as hydrogen and helium clouds, which are gradually drawn to the center by their gravitational pull. As the gas falls inward, it heats up intensely, forming bright disks that emit radiation across various parts of the spectrum, from ultraviolet to infrared and X-rays. This process gives rise to active galactic nuclei, sources of luminosity so intense that they can outshine their entire host galaxies. Observations of this kind were already common with Hubble and other telescopes, but Webb has brought unprecedented detail by detecting these accretion disks in the deep infrared, allowing scientists to study their chemical composition and dynamics in extremely young galaxies. Naked black holes, on the other hand, defy this expectation. They are identified as regions of intense gravitational pull, but lack the luminous disks or large amounts of gas and dust typically associated with such objects. In some cases, the light observed by Webb reveals only the gravitational influence of these black holes on the surrounding stars and space, without clear signs of active feeding. This raises crucial questions. Did these black holes form in gas-poor environments, or did they quickly consume all available matter around them, leaving only a bare nucleus behind? This difference has profound implications for astrophysics. Black holes surrounded by gas and dust tend to grow more quickly as they have abundant fuel at hand. Naked black holes, however, may represent a distinct phase in which growth was interrupted, or perhaps they originated through alternative mechanisms, such as the direct collapse of dense gas clouds that left little residual matter. If confirmed, this diversity of evolutionary tracks could explain why some black holes reached gigantic masses so early, while others remained in less active states. Another interesting point is the impact of observing these two types on the chronology of the universe. The existence of naked black holes in the young cosmos suggests that not all black holes underwent explosive growth phases. Some may have followed quieter paths, growing slowly or remaining stable, until new flows of gas became available for them to feed on. This creates a more varied scenario than previously imagined, where black holes and galaxies do not follow a single line of evolution, but multiple pathways intertwined according to their environments and initial conditions. By identifying both gas-shrouded black holes and naked black holes, James Webb offers a more complex and realistic view of cosmic diversity. It shows that the primordial universe was not homogeneous, but rather a stage for different gravitational and evolutionary experiences. This distinction helps us understand that there is no single template for the birth and growth of cosmic giants. Each black hole carries within itself the particular history of its environment, revealing that the cosmos is as diverse in its origins as it is in its current forms. The presence of supermassive black holes in a universe that had not yet completed its first billion years, is one of the greatest enigmas revealed by the James Webb Space Telescope. How could these gravitational colossi, with masses equivalent to millions or even billions of suns, have arisen in so little time? This question has led scientists to propose different hypotheses, each attempting to fill the gaps left by traditional models. The most classical explanation is gradual growth through gas accretion. In this scenario, stellar origin black holes, formed from the collapse of massive stars with tens of solar masses, would have served as the initial seeds. From there, over hundreds of millions of years, these black holes would have consumed gas, dust, and even stars, eventually growing into supermassive objects. The problem is that even assuming growth rates at the very limit of possibility, the time available between the Big Bang and the observations made by Webb seems insufficient. This makes the hypothesis difficult to sustain on its own, though it remains part of the puzzle. Another possibility is the direct collapse of gas clouds. In this model, extremely dense regions of the primordial universe did not form individual stars, but instead collapsed all at once into black holes with much larger initial masses, from 100,000 to 1 million times the mass of the Sun. These seed black holes would have had an enormous advantage compared to those born from stars, since they would require less time to reach supermassive proportions. This hypothesis has gained traction, especially because Webb has revealed signs of structures that may be linked to these direct collapses. A third hypothesis involves first-generation supermassive stars, known as population 3 stars. Unlike the stars we know today, they could have reached hundreds or even thousands of times the mass of the Sun due to the abundance of pure hydrogen in the primordial universe and the absence of heavy elements that fragment the process of star formation. When collapsing, these stars could have produced black holes already much larger than those formed from modern stars. Although there is no direct evidence yet for the existence of such stars, their theoretical plausibility helps explain the rapid initial growth. There is also the intriguing hypothesis of primordial black holes, which would not have originated from stars or gas clouds, but from quantum fluctuations of the Big Bang itself. According to this idea, regions of extremely high density in the primordial universe could have collapsed into black holes right after the initial expansion, creating massive objects from the very first instance of the cosmos. While speculative and still unconfirmed, some scientists seriously consider this hypothesis, since it elegantly solves the problem of the limited time available for growth. Another factor that may have accelerated the process is violent feeding during early galactic collisions. In the young universe, galaxies were much closer together and interacted frequently. These collisions could have funneled enormous amounts of gas into their centers, feeding black holes far more efficiently than in isolated galaxies. Webb, by observing galactic interactions, even at such distant epochs, provides evidence that this mechanism may have played a decisive role. It is likely that none of these hypotheses alone is sufficient to explain the enigma. The most plausible scenario is that a combination of them occurred in different contexts, generating a diversity of evolutionary trajectories. Some black holes may have started small and grown rapidly thanks to bursts of accretion. Others may have been born already large through direct collapse, and perhaps some came from the very first instance of the universe. James Webb, by providing increasingly precise data, is helping us test these possibilities and narrow down the plausible scenarios. The fact is that regardless of the mechanism, the existence of these giants so early in the universe shows that we still know very little about the first chapters of cosmic history. The proposed hypotheses are attempts to decipher a mystery that challenges our intuition and our most reliable models. But it is precisely in this tension between what is predicted and what is observed that science advances. The primordial black holes of Webb are not just anomalies, they are invitations to rewrite the narrative of cosmic evolution. The detection of supermassive black holes in incredibly young stages of the universe is not merely an astronomical curiosity. It carries profound implications for cosmological models and for high-energy physics. Until now, the standard cosmological model, lambda CDM, provided a consistent narrative for the formation of cosmic structures. First, the cosmic microwave background radiation, then the cooling of gas, followed by the formation of the first stars, and finally the gradual growth of galaxies and their central black holes. The discovery of gravitational giants already formed when the universe was less than 1 billion years old destabilizes this narrative. It is as if we arrived at a library and found complete and detailed volumes on a shelf where we expected only drafts and unfinished manuscripts. One of the most immediate impacts falls on galactic evolution models. The simulations used to describe galaxy formation depend on parameters such as the efficiency of gas cooling, the rate of star formation, and the influence of dark matter. The early presence of supermassive black holes suggests that these parameters may be underestimated or even incomplete. It is possible that the cooling of primordial gas was more efficient than previously thought, or that black holes grew more violently and rapidly in bursts triggered by galactic collisions. These adjustments may seem small, but in practice, they demand a deep revision of the equations that describe cosmic evolution. Another crucial point is linked to high-energy physics, ARM. The formation and accelerated growth of black holes in the young universe highlight extreme processes of matter accretion and energy release. Accretion disks around these objects heat gas to millions of degrees, emitting radiation in multiple wavelengths, including X-rays and intense ultraviolet. This radiation, in turn, influences the intergalactic medium and may have accelerated cosmic reionization. This means that black holes were not mere spectators of the primordial universe, but active agents in transforming diffuse plasma into a medium transparent to light. This direct participation of black holes in the evolution of the cosmos must be integrated into models of fundamental physics. There is also an impact on our understanding of dark matter and dark energy. The early formation of supermassive black holes suggests that the distribution of dark matter in the early universe may have been more concentrated and denser than models indicated. This could have provided the gravitational scaffolding necessary to accelerate the clumping of gas and create these giants in a short time. If confirmed, it may be necessary to revise not only how we simulate dark matter, but even its nature. Could it interact subtly with ordinary matter under extreme conditions? Might there be particles or mechanisms not yet discovered that could explain these discrepancies? In addition, there are implications for the theory of general relativity. Although Einstein's theory has been confirmed in countless tests, black holes in the primordial universe offer a new extreme laboratory to test its limits. The formation and evolution of these objects may reveal subtle discrepancies that indicate the need for a more comprehensive theory, one capable of unifying gravity with quantum mechanics. This quest for a quantum theory of gravity is one of the greatest challenges of contemporary physics, and black holes in the early universe may be key pieces of this puzzle. Finally, it is important to emphasize that these impacts are not limited to technical revisions of models. They represent a shift in perspective about the role of black holes in cosmic history. Once viewed as consequences of stellar evolution, they now appear as protagonists from the very first chapters of the universe. This changes not only our understanding of chronology, but also the very narrative of cosmic evolution. The James Webb Telescope, by revealing these early giants, forces us to rewrite entire sections of the Book of the Cosmos and to acknowledge that we are still far from fully understanding the fundamental laws that govern the universe. Dark matter remains one of the greatest enigmas of contemporary science. We know that it does not emit, reflect, or absorb light, but its presence is evident through the gravity it exerts on the visible structures of the universe. The James Webb Space Telescope, although unable to detect dark matter directly, is offering indirect evidence that reinforces its existence and helps to map its distribution. Each observation of gravitational lenses, such as Einstein's cross, each measurement of galaxy rotation, and each analysis of brightness in distant structures is, in practice, a silent testimony to the role of this invisible substance. One of the most powerful indirect pieces of evidence observed by Webb lies in the distortions of light from background galaxies. When the telescope captures arcs, crosses, and rings formed by gravitational lenses, it is not merely recording a beautiful phenomenon. It is mapping the gravitational field of regions where most of the mass is not visible. These effects require the presence of massive halos that cannot be explained solely by observable stars and gas. The case of Einstein's cross is exemplary. The cross only forms with the observed symmetry if there is a gigantic halo of dark matter surrounding it. Thus, each gravitational lens recorded by Webb works as an indirect detector of this invisible matter. Another line of evidence comes from the extremely young galaxies revealed by Webb. Many of them display masses and luminosities far greater than models predicted for such early periods. For such growth to have occurred so quickly, an additional gravitational mechanism would be required to attract large amounts of gas in short time intervals. The most consistent hypothesis is that dense dark matter halos acted as gravitational scaffolds, pulling baryonic matter, hydrogen and helium, into regions of high concentration, accelerating the formation of massive galaxies. This link between the distribution of dark matter and the early emergence of galaxies is one of the central points revealed by Webb's observations. Furthermore, the telescope showed that many distant galaxies display signs of organization into protoclusters, connected by filaments stretching millions of light years. This invisible cosmic web, predicted by simulations and now reinforced by observations, is sustained precisely by dark matter. Without it, the universe would be a diffuse and disorganized place, with galaxies isolated and unconnected. The existence of these filaments, revealed indirectly by the distribution of galaxies, is further evidence that most of the matter in the cosmos cannot be seen, only felt by its gravitational effects. Indirect evidence also appears in the internal dynamics of galaxies. Webb has managed to measure rotation curves in very distant systems, showing that stars in the outer regions move at much higher speeds than they should if only visible matter were present. This same effect had already been observed in closer galaxies, but now for the first time we have records in extremely early epochs of the universe. This reinforces the idea that dark matter did not emerge late, but was already present from the very beginning, shaping the growth and stability of cosmic structures. Finally, there are the more subtle clues, such as the diffuse glow of the cosmic background and the distribution of infrared radiation captured by Webb. In some cases, the intensity of brightness in distant regions can only be explained if we consider that there is more gravitational mass pulling matter into galaxies than what we can observe directly. This constant discrepancy, repeated in different contexts, is a hallmark of the presence of dark matter. Thus, even though James Webb cannot see dark matter directly, each of its observations works as a mirror of what we cannot see. It confirms that most of the universe is made of something invisible, silent and mysterious, yet absolutely essential. These indirect pieces of evidence are the threads that allow us to weave the fabric of the invisible, revealing that behind the beauty of cosmic images lies a much deeper reality, that of a universe sustained by a structure completely beyond ordinary vision. One of the most remarkable advances brought by the observations of the James Webb Space Telescope is the confirmation of the central role of dark matter halos in the formation of the first galaxies. These halos act as invisible scaffolds, structures made of pure gravity that gather and trap baryonic matter, the hydrogen and helium that make up stars, in specific regions of space. Without these scaffolds, ordinary matter would have spread diffusely throughout the cosmos, never clumping into stable systems. That is why dark matter halos are considered the foundation of cosmic architecture, responsible for giving shape to the first complex structures of the universe. Webb's observations of extremely young and massive galaxies confirm this function. For such large systems to exist only a few 100 million years after the Big Bang, there had to be a mechanism capable of drastically accelerating the clumping of primordial gas. The most consistent explanation is that these objects formed in regions where dark matter halos were already present, pulling and concentrating baryonic matter into smaller and denser volumes. This additional gravity provided the necessary push for the first stars and galaxies to emerge much earlier than traditional models predicted. Another point revealed by Webb is the organization of these early galaxies into filaments and protoclusters. This pattern is not random, but corresponds exactly to what cosmological simulations predicted for the sun-cosmic web of dark matter. At the intersections of these invisible filaments, gravitational density is higher, functioning as natural nurseries for galaxy formation. Webb, by mapping galaxies at such primitive stages, confirmed that dark matter halos were not only present, but were already outlining the skeleton of the universe we see today. The relationship between halos and early galaxies also helps explain the stability of these structures. Without the invisible mass anchoring them, Young galaxies would not have been able to keep their stars cohesive for long. They would have quickly dispersed, leaving only unstable clusters. Yet, what we see in Webb's images are cohesive systems, with dense cores and even signs of chemical maturity. This is only possible because the gravity exerted by dark matter halos keeps the stars bound, preventing them from escaping. It is as if galaxies were small islands of light sustained by invisible oceans. Another interesting aspect is that these halos seem to have allowed a surprisingly high efficiency in star formation. By concentrating gas in specific regions, they accelerated the process of hydrogen cooling and collapse, giving rise to large-scale star formation bursts. This mechanism explains, in part, why Webb found such bright galaxies at such early epochs. The presence of dense halos ensured that the process was not gradual but explosive, rapidly producing entire populations of stars. In summary, the James Webb observations reinforce a central idea of modern cosmology. Galaxies are not isolated entities that appeared by chance, but direct offspring of dark matter halos that have shaped the cosmos since the beginning. Every star we see, every distant galaxy Webb records, is in fact the visible side of a much larger and invisible structure. The relationship between halos and early galaxies not only confirms theoretical predictions, but also reveals how much we still need to learn about the nature of this matter that does not shine, but sustains practically everything that exists. Gravitational lenses are among the most powerful tools of modern astrophysics, and the James Webb Space Telescope has turned this resource into a true machine for mapping the invisible. The principle behind this phenomenon comes directly from Albert Einstein's general theory of relativity. Gravity is not just a force of attraction, but a curvature of space-time itself. When the light of a distant object passes near a massive galaxy or cluster, its path is bent, as if it were going through a cosmic lens. The result is distorted, magnified, and even multiplied images of the background object, phenomena that Webb is able to capture in unprecedented detail. The scientific value of these lenses goes far beyond the visual spectacle. By analyzing the intensity and symmetry of the distortions, astronomers can calculate the amount of mass involved in the process. In almost every case, the gravity required to explain the distortions is much greater than what can be attributed to visible matter. This means that most of the mass responsible for the lens is made of dark matter. In this way, each arc or cross observed by Webb functions as a marker of the presence of this invisible substance. It is as if the universe were giving us visual clues to map something that would otherwise be undetectable. One of the most emblematic examples was the detection of the Einstein's cross B, in which four identical images of the same distant object appear around an intermediate galaxy. Webb showed that for that cross to form so symmetrically, a gigantic halo of dark matter had to be involved. This case was not just a curiosity, but a direct confirmation that invisible halos are real and that their distribution can be studied through these lensing effects. Moreover, Webb is using gravitational lenses strategically. Instead of only observing the objects that create the lens, it investigates the distant galaxies that are magnified by it. Thanks to this effect, the telescope can see galaxies so ancient and faint that without the lens they would be invisible even to its extraordinary sensitivity. This means that the very gravity of the universe becomes an extension of the telescope's power, acting as a natural instrument that multiplies its investigative capacity. Another crucial point is that the lenses allow scientists to map the distribution of dark matter on different scales. By observing several lensing systems scattered across the sky, researchers can build an invisible atlas, identifying where halos are more concentrated and how they are distributed along the cosmic web. This kind of mapping is essential for testing theories about the nature of dark matter, helping to verify whether it is truly cold and smooth, as the standard model predicts, or whether it shows irregularities that could indicate new physics. Gravitational lenses also offer a unique advantage, the possibility of measuring cosmic distances with great precision. Since the time light takes to travel, the different distorted paths can vary. It is possible to calculate not only the mass of the lens, but also fundamental parameters of the universe's expansion. By recording these time delays in multiple systems, Webb contributes to refining the measurement of the Hubble constant, which describes the cosmic expansion rate. one of the most debated topics in cosmology today. Ultimately, gravitational lenses have turned Webb into a mapper of the invisible. Each luminous arc, each cross and each ring revealed is not just an aesthetic spectacle but concrete evidence of the presence and behavior of dark matter. By uniting Einstein's relativity with the most advanced technology in astronomy, Webb is deciphering what was once only a hypothesis, the existence of a hidden structure that has sustained and shaped the universe since its beginnings. Dark matter is perhaps the greatest enigma of modern cosmology. Since the mid-20th century, when Vera Rubin demonstrated that the rotation speeds of galaxies could not be explained solely by visible matter, it has been clear that the universe hides something fundamental. Today we know that about 85% of all matter in the cosmos is made of this invisible substance. Yet despite its colossal importance, we still do not know what it really is. The James Webb Space Telescope, by offering indirect evidence on unprecedented scales, reinforces the mystery. We see its gravitational effects, but never the substance itself. There are several hypotheses about the nature of dark matter. The best known is that of WIMPs, weakly interacting massive particles. These particles would be invisible to light, but massive enough to generate the gravitational effects observed. Despite decades of searches in underground experiments and particle accelerators, no direct detection has yet been confirmed. Another well-studied hypothesis is that of an axions, extremely light particles predicted by some quantum physics theories, which could behave like waves and fill the universe diffusely. More recently, ideas have emerged about even more exotic particles, such as sterile neutrinos, or unknown states of matter that do not interact with electromagnetism in any way. An alternative line of thought questions whether we really need new particles to explain dark matter. According to this approach, perhaps gravity does not work exactly as we believe on cosmic scales. Theories known as modified gravity suggest that the effects we attribute to dark matter could be the result of gravitational laws slightly different from those predicted by Einstein. However, these theories face difficulties because they cannot explain all the phenomena observed, especially the patterns of gravitational lenses recorded by James Webb, which fit better with the hypothesis of the presence of invisible mass. Webb was not designed to detect particles directly, but its observations provide critical clues. By showing gigantic halos of invisible matter supporting early galaxies, it reinforces the idea that dark matter is not just a mathematical invention, but something real and distributed on a large scale. The symmetry and consistency of the gravitational effects observed are strong indications that this substance has a stable, universal, and fundamental nature. This places pressure on particle physics. If it exists in such abundance, we must find a concrete explanation in the laboratory. Another point raised by Webb's observations is the link between dark matter and cosmic formation. The way it is distributed in space, in filaments and halos, seems essential for the evolution of galaxies. This suggests that dark matter is not just invisible mass, but also a fundamental structure, a kind of scaffolding of the universe. Without it, there would not have been enough time for stars and galaxies to form. This structural role is so profound that some scientists propose dark matter may be related to fundamental fields of physics, perhaps connecting gravity and quantum mechanics at a still unknown level. The enigma, therefore, remains open. What we know is that dark matter exists and dominates most of the cosmos's mass. What we do not know is its composition, its origin, and its place in the fundamental laws of physics. James Webb does not give us the definitive answer, but it broadens the scope of the questions, showing that it was already present in the first billions of years and that its influence was decisive from the beginning. Each new image captured by the telescope is proof of its silent presence and a reminder that the universe is far more mysterious than our imagination can encompass. The James Webb Space Telescope was not built specifically to hunt for dark matter particles, but its observations are becoming key pieces in the attempt to solve this cosmic mystery. Webb's strength lies in its ability to see the universe with a level of detail never before achieved, especially in very ancient epochs, when the first cosmic structures were forming. It is precisely in this primordial scenario that the influence of dark matter becomes clearer, shaping galaxies, clusters, and even the invisible cosmic web that connects the entire cosmos. One of the most powerful ways Webb contributes is through the study of gravitational lenses. By observing arcs, crosses, and rings formed by the light of distant galaxies, the telescope can map the distribution of invisible mass that sustains these phenomena. These maps are compared with predictions from cosmological simulations, helping to confirm or rule out different hypotheses about the nature of dark matter. For example, if dark matter were made of very light particles that behave more like waves, the distribution of halos should be more diffuse. On the other hand, weakly interacting massive particles would create denser structures. The precision of Webb's images is allowing astronomers to distinguish these subtle differences. Another central point is the analysis of early galaxies. Webb has revealed surprisingly large and massive galaxies at times when models indicated they should not exist. The best explanation for this accelerated growth is the presence of extremely dense dark matter halos, which rapidly attracted and concentrated primordial gas. By studying these galaxies, scientists are obtaining valuable clues about how dark matter was distributed in the early universe and how its gravity influenced the formation of the first structures. This helps us understand not only the amount of dark matter, but also its fundamental properties. Webb also indirectly contributes to investigating dark matter by measuring the rate of expansion of the universe with great precision. The Hubble constant, which describes the speed of cosmic expansion, is one of the most important parameters in cosmology and lies at the center of one of today's biggest controversies. Different measurement methods have produced conflicting values. Since dark matter plays an essential role in this expansion, refined measurements made by Webb in gravitational lenses, distant supernovae, and primitive galaxies may help clarify whether the discrepancies are the result of errors in the methods or whether they point to new physics directly connected to the nature of dark matter. Another promising area is the study of cosmic Reionization, the period when radiation from the first stars and black holes transform neutral hydrogen into ionized plasma, making the universe transparent to light once again. The speed at which this process occurred suggests that dark matter may have played a more active role than previously imagined, accelerating the formation of luminous sources capable of reionizing the cosmos. Webb, by mapping this period in detail, is providing critical information to connect the behavior of dark matter to the earliest phases of cosmic evolution. Finally, it is important to highlight that Webb does not work alone. Its discoveries are complemented by terrestrial experiments that search for dark matter particles in underground laboratories and by other observatories that measure radiation at different wavelengths. But it occupies a unique place. It is the window that allows us to see how dark matter acted in the early universe. Instead of just looking for hypothetical particles, Webb shows us their macroscopic effects, revealing the invisible architecture that shapes galaxies and the very destiny of the cosmos. In summary, James Webb does not directly solve the enigma of dark matter, but it illuminates the possible paths. It does not deliver the final answer, but it provides the most detailed clues ever obtained. Every Einstein cross, every luminous arc, every early galaxy recorded by the telescope is an invisible signature that brings us closer to the moment when we will finally be able to decipher what most of the universe's matter is made of. The standard cosmological model, known as lambda CDM is today the backbone of cosmology. It combines Albert Einstein's theory of general relativity with the presence of cold dark matter and dark energy, explaining everything from the cosmic microwave background radiation to the large-scale distribution of galaxies. For decades, this model has proven to be incredibly successful, providing consistent predictions that have been confirmed by observations. However, the revelations of the James Webb Space Telescope have begun to expose tensions that can no longer be ignored. Early galaxies, supermassive black holes in the young universe, and the need for gigantic dark matter halos are creating cracks that may force profound adjustments or even open the door to new theories. One of the most critical issues is the early appearance of massive galaxies. According to lambda CDM, structure formation should be gradual, with small galaxies appearing first and merging over billions of years to form larger systems. But Webb has shown galaxies with masses of billions of suns at times when the universe was only a few 100 million years old. This not only contradicts the predicted chronology, but also raises the question of whether the model is underestimating the efficiency of star formation and the concentration of dark matter in the primordial universe. Another point of tension lies in early supermassive black holes. Lambda CDM predicts that black holes form from small seeds, growing slowly through gas accretion, but Webb has found gravitational giants already fully formed when the universe was still very young. This suggests that alternative mechanisms, such as the direct collapse of gas clouds, may have been at play but are not robustly incorporated into simulations based on the standard model. This discrepancy casts doubt on whether the laws we use to describe structure growth can be applied universally across all cosmic epochs. There is also the issue of the Hubble constant, which measures the expansion rate of the universe. Different calculation methods have provided different values, creating the so-called Hubble tension. Webb's observations may deepen this divergence, since distances measured through gravitational lenses and distant supernovae do not always match the predictions of the Lambda CDM model. If this discrepancy persists, it could indicate that dark energy, responsible for the acceleration of cosmic expansion, is not as simple as the model suggests, or that there is physics not yet incorporated into our equations. In addition, Webb's dark matter mapping diagram shows halos larger and denser than expected in certain regions. This could mean that cold dark matter does not behave exactly as the models describe, or that we need to consider variations in its nature, such as the possibility of particles with different properties at quantum scales. These tensions do not invalidate Lambda CDM, but suggest that it may be an incomplete approximation, useful in many contexts but unable to explain all the details revealed by new observations. These tensions should not be seen as a threat, but as opportunities. The history of science shows that great advances arise when established models encounter data that do not fit. This was the case with Mercury's orbit, which led to general relativity, and it may be happening now with James Webb's discoveries. If Lambda CDM needs to be adjusted, or even replaced, it will be because the universe itself is forcing us to expand our understanding. And what today appear as cracks may, in the future, become a new and even stronger foundation for cosmology. If dark matter already represents a monumental challenge for cosmology, dark energy is even more enigmatic. It is estimated to make up about 70% of the universe's content and is thought to be responsible for the acceleration of cosmic expansion. The Lambda CDM model assumes that this dark energy is a cosmological constant, a uniform and immutable force that acts the same everywhere in space and at all times. However, recent observations from the James Webb Space Telescope are putting pressure on this simplified view, raising the possibility that dark energy is more dynamic and complex than we once supposed. One of the central issues is the so-called Hubble constant tension. This parameter, which measures the universe's rate of expansion, has been calculated in different ways, resulting in conflicting values. Measurements based on the cosmic microwave background yield a lower value, while observations of supernovae and nearby galaxies point to a higher one. Webb, by measuring cosmic distances using gravitational lenses and supernovae at distant epochs, may help resolve this discrepancy, or paradoxically confirm it even more clearly. If the values remain in disagreement, it will be a sign that dark energy may not be a simple constant, but rather a variable entity that has changed throughout cosmic history. Webb's observations also suggest that the early formation of massive galaxies and supermassive black holes may have been influenced by dark energy. This is because the universe's expansion rate in its first billions of years defines how quickly matter can clump together to form structures. If dark energy was weaker or stronger at different times, it would have had a direct impact on galaxy evolution. The fact that Webb is finding such large structures in such early periods may indicate that dark energy did not behave exactly as the Lambda CDM model predicts. Another line of investigation is the relationship between dark energy and the cosmic web of dark matter. Webb's observations show that the invisible filaments connecting galaxies formed quickly and on large scales. This raises the question, could dark energy beyond driving expansion also influence how this web is organized? Some cosmologists believe that dark energy may be linked to still unknown fundamental fields, possibly connected to quantum physics, and that its action may vary in intensity with both time and space. It is important to note that Webb does not directly measure dark energy, but it provides crucial data for testing it. By recording the position, age, and distribution of extremely ancient galaxies, it provides reference points that can be used to reconstruct the expansion rate in different epochs. When compared with the predictions of the standard model, these data may reveal whether dark energy really behaves like a constant or whether new theories are needed to describe it. Ultimately, James Webb is widening the cracks already present in the lambda CDM model. Dark energy, once considered an elegant and simple solution, is beginning to appear as an even greater mystery than we imagined. Perhaps it is dynamic. Perhaps it is connected to hidden dimensions or even to unknown interactions between gravity and fundamental particles. Whatever the answer may be, Webb's observations are making it clear that we can no longer treat dark energy as a solved black box. It is an open enigma, and each new discovery expands the need for deeper answers. Cosmological simulations have always been fundamental tools for modern science. With the help of supercomputers, astronomers recreate the evolution of the universe from the very first instance after the Big Bang to the formation of the galaxies we observe today. These models, based on the lambda CDM paradigm, allowed scientists to predict the large-scale distribution of galaxies, the formation of the cosmic web of dark matter, and even the chronology of Reionization. However, the observations of the James Webb Space Telescope have begun to expose flaws and significant discrepancies between what the models predicted and what is actually being seen in such remote epochs. Classical simulations indicated that, in the first 500 million years, the universe should have been populated by small, incipient galaxies with low mass and modest luminosity. However, Webb has found galaxies already gigantic, with billions of solar masses and supermassive black holes in full activity. These findings force scientists to revisit the algorithms used in simulations, incorporating new mechanisms of formation and growth. Among them stand out hypotheses of direct collapse of gas clouds, much higher efficiency in initial star formation, and the presence of denser dark matter halos than previously imagined. Another challenge for simulations is the diversity of early galaxies. While some appear already mature and massive, others seem extremely compact and rich in heavy elements, suggesting several generations of stars within a very short time span. This mosaic of structures is far more varied than computational models predicted. To deal with this, simulators are expanding the parameters of simulations, testing everything from new gas cooling laws to more complex feedbacks from supernovae and black holes. This demonstrates how science works in cycles. Theory guides observations, and observations force theory to reinvent itself. Supercomputers are also being used to explore alternative scenarios for the nature of dark matter and dark energy. If dark matter is not exactly cold, as the standard model assumes, but has different properties, such as lighter particles or subtle interactions, the formation of cosmic structures would change. Simulations are testing these possibilities to verify whether any adjustment can reproduce Webb's data. Similarly, hypotheses of dynamic dark energy are being incorporated into some models to see how variations in its intensity could affect expansion and the growth of galaxies. Another aspect is that Webb is providing data on a scale of detail that requires increasingly high-resolution simulations, whereas before it was possible to work only with billions of particles representing masses of gas and dark matter. It is now necessary to model processes on smaller scales, such as the individual formation of stars and the dynamics of gas around black holes. This requires a technological leap in processing power and refinement of algorithms. Many of these projects are underway, with simulations that consume entire months of supercomputer time to generate results that can be compared with Webb's images and spectra. Finally, it is important to emphasize that simulations are not just theoretical exercises. They work as virtual laboratories. Instead of waiting billions of years to observe the evolution of a galaxy, scientists can fast-forward time in a computer and check how different parameters alter the results. The confrontation between what Webb sees and what the models reproduce is today one of the most fertile areas in cosmology. Each discrepancy is not just an error, but a window to discover which physical processes are still missing in our understanding. Thus, The role of cosmological simulations in the face of new data is twofold. On the one hand, they are in crisis, challenged by unexpected discoveries. On the other hand, they are in full transformation, incorporating new concepts and expanding the limits of scientific imagination. James Webb not only observes the cosmos, it redefines the virtual experiments we use to understand it, opening the way for a future in which theory and observation walk ever more closely together. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by showing us the universe in detail never before seen. It was with Hubble that we recorded the famous Hubble Deep Field, revealing thousands of galaxies in a small region of the sky that appeared to be empty. For 3 decades, Hubble provided fundamental data for cosmology, helping confirm the acceleration of the universe's expansion and consolidating the lambda CDM model. However, even at its peak, Hubble had clear limitations. Its vision was restricted mainly to the visible and ultraviolet spectrum, which prevented it from peering deeply into regions obscured by dust and, most importantly, from effectively probing the primordial universe. This is where the James Webb Space Telescope brought a revolution. With its instruments optimized for the infrared, Webb can observe galaxies whose light has traveled more than 13 billion years to reach us. This means it can look back in time to periods when the universe was only a few hundred million years old. It is in this unexplored region that the greatest cosmological tensions emerged. While Hubble had already identified very distant galaxies, Webb's data showed that they were more massive, more numerous and more mature than expected, widening the gap between theory and observation. A direct comparison shows the difference in reach between the two telescopes. Hubble could detect some of the earliest galaxies, but with weak signals and limited information. Webb, however, revealed these same structures in detail, exposing their luminosity, chemical composition, and even signs of central black holes. What was once just a poorly defined shadow became a clear image, and with that clarity came contradictions. The tensions that already existed discreetly in Hubble's data turned into explicit challenges with Webb. Another point of contrast lies in the study of gravitational lenses. Hubble recorded many cosmic arcs and rings, confirming the presence of massive dark matter halos. But it was Webb that managed to analyze these structures with enough precision to calculate the density and profile of those halos on unprecedented scales. The result was the realization that some halos are even larger and more concentrated than models predicted, increasing tensions with the lambda CDM paradigm. Furthermore, Webb expanded the scope of the so-called Hubble tension. Hubble had helped reveal the discrepancy in the values of the Hubble constant obtained by different methods. But Webb, by measuring cosmic distances even farther away and analyzing gravitational lenses with greater detail, began refining those numbers in such a way that the discrepancy did not disappear. On the contrary, it became more evident. This reinforces the possibility that the problem is not just a measurement error, but an indication that something in the standard model is incomplete. This comparison makes it clear that James Webb did not come to replace Hubble, but to take it to the next level, a level where enigmas can no longer be ignored. Hubble showed us that the universe was larger, more dynamic, and more accelerated than we had imagined. Webb, in turn, is showing us that it is also earlier, denser, and more mysterious than the models can explain. If Hubble was the telescope that consolidated lambda CDM, Webb may well be the one to open the way for the next great revolution in cosmology. Cosmic Reionization is a fundamental milestone in universal chronology, as it represents the transition between a dark cosmos and a universe transparent to light. After the Big Bang, when the universe was only a few 100,000 years old, protons and electrons combined to form neutral hydrogen atoms, filling space with an opaque fog. This period, known as the Cosmic Dark Ages, lasted until the first stars and galaxies formed. The ultraviolet radiation emitted by these first luminous sources began to reionize the neutral hydrogen, separating protons and electrons and making the universe transparent to light on a large scale. This process, called reionization, occurred between 300 and 800 million years after the Big Bang. The James Webb Space Telescope, by observing the universe during this critical time interval, is providing the best evidence ever obtained about how and when reionization occurred. One of the most intriguing discoveries is that the massive galaxies revealed by Webb present much earlier than expected, may have played a central role in this process. Their intense bursts of star formation and the presence of active black holes would have emitted colossal amounts of ionizing radiation, accelerating reionization at a faster pace than previous models suggested. This means the universe may have become transparent much earlier than the predicted timeline. Another point revealed by Webb is the diversity of sources responsible for reionization. Previously, it was believed that only the first generation of stars played this role. Now observations suggest that extremely bright young galaxies and even quasars powered by early black holes may have contributed significantly. This broadens the reionization scenario, showing that it was not merely a gradual process of isolated stars, but a collaboration of different cosmic mechanisms working together to transform the universe. Webb is also helping to map reionization in spatial terms. Instead of occurring uniformly across the cosmos, the data suggest it was an irregular and localized process. Bubbles of ionized gas formed around the first galaxies and grew until they merged, clearing the fog of neutral hydrogen. Webb's images of distant galaxies in different stages reveal this mosaic of ionized and non-ionized regions, allowing scientists to reconstruct the process in detail. It is like watching the first cities appear on a dark map and gradually illuminate the entire territory. This new understanding has direct implications for cosmological tensions. If reionization occurred earlier and faster than predicted, it may explain why Webb found massive galaxies so early. The presence of dense dark matter halos, combined with the intense emission of ionizing radiation, would have created the conditions for the universe to evolve at an accelerated pace. This scenario, however, requires adjustments to the models, since the traditional lambda CDM predicted a slower and more gradual timeline. Finally, cosmic reionization is more than a chapter in universal history. It is the moment when the cosmos became visible on a large scale. Without it, the light from the first stars and galaxies would not have traveled through space to reach us. Webb, by directly probing this period, not only confirms that reionization occurred, but also shows that it was more complex, faster, and more diverse than we imagined. Each piece of data brought by the telescope is a new clue to understanding how the universe transitioned from primordial darkness to the immense luminous tapestry we observe today. Quasars are some of the most intense energy sources in the universe, and their discovery in the 20th century radically changed the understanding of astrophysics. They are active galactic nuclei powered by supermassive black holes that, while swallowing large amounts of matter, release radiation at such extreme levels that they can outshine the entire galaxy in which they are located. In the context of cosmic reionization, quasars represent one of the most important candidates to explain how quickly the universe transitioned from opaque to transparent to light. The James Webb Space Telescope, by observing signs of these objects at incredibly early times, has brought new evidence that they may have played a crucial role in this process. One of the main contributions of quasars lies in the emission of ionizing ultraviolet radiation. When the gas around the central black hole is accelerated and heated to millions of degrees, it emits radiation capable of stripping electrons from hydrogen atoms, transforming neutral gas into ionized plasma. This radiation spreads through the intergalactic medium, creating bubbles of transparency that expand over time. Webb has revealed quasars in very young stages of the cosmos, indicating that they were active already within the first billions of years. This means they may have provided a significant amount of ionizing radiation alongside the first stars, accelerating the reionization process. Another important point is that quasars not only illuminate the universe, but also help scientists map the state of the intergalactic gassing during reionization. The intense light of these objects travels vast distances and interacts with hydrogen along the way. When that light reaches us, it carries fingerprints of the absorption suffered by the gas, known as the Lyman alpha forest. Webb, with its ability to record detailed spectra, is allowing these signatures to be analyzed at earlier epochs, revealing how reionization spread across different regions of the cosmos. The role of quasars in reionization, however, is not simple. Although they emit enough radiation to transform large volumes of gas, there remains the issue of population density. Webb has shown that early quasars existed, but we do not yet know how many there were. or if their number was sufficient to reionize the universe on their own. Many scientists believe that quasars worked in concert with young galaxies in a collaborative process. While the stars in these galaxies provided ionizing radiation on a local scale, quasars expanded the reach of this effect, enlarging ionization bubbles that eventually merged. There is also the possibility that quasars influenced the pace of reionization indirectly. By releasing colossal amounts of energy, they may have heated the intergalactic medium, altering the dynamics of the gas and impacting the rate at which new stars formed. In this sense, their role was not only to illuminate and ionize, but also to shape the physical conditions of the cosmos in a decisive period of its history. Ultimately, James Webb's observations are repositioning quasars as protagonists in the scenario of early reionization. They were not mere supporting actors to pioneering stars, but cosmic sources of energy capable of transforming entire regions of the universe. By revealing their presence in such remote times, Webb confirms that supermassive black holes and their luminous activity were central pieces in the puzzle of cosmic evolution. Each spectrum collected by the telescope is a reminder that at the heart of the oldest galaxies, voracious black holes were already shaping the fate of the cosmos. The ionizing radiation that permeated the universe during cosmic reionization not only cleared the primordial fog, but also played a decisive role in the evolution of the first galaxies. The James Webb Space Telescope has shown that, in the first billions of years, massive stars, quasars, and active black holes emitted enough radiation to ionize vast regions of neutral hydrogen, creating bubbles of transparency in the cosmos. This process, however, was not neutral for the galaxies themselves. It shaped their trajectories, influenced their ability to form new stars, and altered the chemistry of the interstellar medium. One of the main effects of ionizing radiation was the high heating of gas. When hydrogen was ionized, the increased energy prevented it from condensing easily into new stars. This meant that, in some regions, star formation was suppressed or delayed, creating galaxies with dormant periods in their evolution. On the other hand, in dense regions where the gravity of dark matter halos was intense, the heated gas could accumulate again, triggering bursts of star formation on explosive scales. The result was an uneven growth rate, with some galaxies growing rapidly, while others remained small and faint for long periods. Another important impact was the chemical alteration caused by this radiation. The interaction between ionizing light and gas accelerated reactions that led to the formation of heavier elements and simple molecules, such as molecular hydrogen, essential for the formation of cool stars. Webb, by detecting spectral signatures in distant galaxies, revealed that some of them already contained metals, elements such as oxygen and carbon, in surprising quantities for such early epochs. This suggests that ionizing radiation helped enrich the interstellar medium rapidly, changing the composition of future generations of stars and planets. In addition, ionizing radiation had a direct impact on galactic morphology. Stellar winds and jets from supermassive black holes pushed ionized gas out of galaxies, creating diffuse halos and feeding the intergalactic medium. This constant exchange of matter between galaxies and their environment not only redistributed energy, but also influenced how galaxies organized themselves over time. Webb revealed structures that appear very mature, with well-defined disks and signs of stellar clusters, indicating that radiation and energy flows played a fundamental role in shaping these forms. Finally, the impact of ionizing radiation goes beyond the local scale. As it spread throughout the universe, it established a balance between the formation of new stars and the control of gas density. Without this balance, the universe could have formed stars in a chaotic and uncontrolled way. Instead, the reionization process driven by this radiation created conditions for a more organized cosmic evolution, guided by the interaction between light, matter, and gravity. James Webb, by observing this critical period, shows that ionizing radiation was not just a side effect of the formation of the first luminous sources, but an active agent that shaped the destiny of galaxies. The term feedback in astrophysics describes how stars and black holes return energy and matter to the medium around them, influencing galactic evolution and even the structure of the cosmos on a large scale. The James Webb Space Telescope, by observing the first galaxies, showed that feedback was not just a secondary detail, but a central mechanism that shaped the young universe. Each supernova explosion, each stellar wind, and each jet launched by supermassive black holes acted as an engine capable of transforming entire environments. In the case of massive stars, feedback begins during their lifetime. Powerful winds expel layers of gas at speeds of hundreds of kilometers per second, enriching the interstellar medium with heavy elements such as oxygen, carbon, and iron. When these stars die in supernova explosions, the impact is even greater. Shock waves sweep through the galaxy's gas, compressing some regions and stimulating new star formation, while dispersing others and hindering the process. This cycle of destruction and creation was essential for accelerating the chemical diversity of the cosmos and preparing the ground for future stellar generations. In the case of supermassive black holes, feedback reaches even more colossal proportions. When matter falls into their accretion disks, enormous amounts of energy are released in the form of radiation and relativistic jets. Webb revealed signs of these processes in extremely young galaxies, showing that black holes were already active and playing the role of regulators of galactic growth. In some cases, their jets heated gas and prevented new star formation. In others, by colliding with nearby gas clouds, the jets compressed the material and triggered bursts of star formation. This duality of black hole feedback, sometimes inhibiting, sometimes stimulating, is one of the factors that makes their influence so complex. A crucial point revealed by Webb's observations is that feedback did not occur on isolated scales. It operated on multiple simultaneous layers, from the internal chemistry of gas clouds to the dynamics of entire galaxies, and by extension, the evolution of the cosmic web. The young universe was not a static and predictable environment, but a boiling space where energy and matter circulated in rapid cycles. This vision contrasts with the earlier idea that the first galaxies were merely passive accumulators of stars and gas. On the contrary, they were turbulent laboratories, constantly reshaped by the feedback from their own energy sources. The impact of this process on cosmological modeling is profound. Simulations that do not properly account for feedback tend to overestimate the number of stars formed and underestimate the chemical diversity of galaxies. James Webb, by revealing early galaxies more complex than expected, is forcing adjustments in models, including more sophisticated parameters of stellar and black hole feedback. These adjustments are not technical details, but essential pieces to explain how the universe managed to evolve so quickly and in such an organized way. Ultimately, stellar and black hole feedback was the mechanism that set the rhythm of cosmic growth. Without it, the universe could have developed in a disordered way, with overcrowded galaxies or, conversely, stagnant ones. With it, a dynamic balance between creation and destruction emerged, allowing the cosmos to structure itself on a large scale. Webb, by illuminating this process, shows us that the young universe was not only the stage for star and galaxy formation, but also the setting of an intense dialogue between energy and gravity, light and shadow, chaos and order. Since the James Webb Space Telescope began sending its first images, the impact was immediate, not only on the public, but also on the scientific community. On one hand, there was consensus in recognizing that Webb represents the greatest leap ever taken in astronomical observation, capable of seeing the universe at epochs and in details that were previously inaccessible. On the other hand, intense controversies arose because much of the data collected does not seem to fit comfortably within the predictions of the standard cosmological model. This tension between enthusiasm and discomfort is one of the engines that drives science forward. Among the points of due consensus, one of the most notable is the confirmation of the crucial role of dark matter halos in the formation of the first galaxies. Webb's observations of gravitational lenses and early galaxies reinforce that there is an invisible mass structuring the cosmos. Another important consensus is the aesthetic and technical value of the telescope's images, which not only inspire, but also provide extremely precise spectral and photometric data. The community also agrees that Webb has opened a new era of observational cosmology, comparable only to what Hubble represented in the 1990s. However, the past points of controversy soon emerged. One of the most discussed is the detection of very early massive galaxies, some so large and mature that they should not exist so soon according to the models. While some scientists argue that these objects are real and require theoretical adjustments, others suggest that they may be overestimated due to uncertainties in distance and mass measurements. The debate revolves around the reliability of the initial estimates and the need for more refined spectroscopic studies, which Webb is progressively carrying out. Another controversial theme is the interpretation of primordial supermassive black holes. For some, they are proof that we need to consider alternative formation mechanisms, such as the direct collapse of gas clouds. For others, their existence can still be explained within the standard model, as long as one admits extremely accelerated growth rates. This clash is not only technical, it touches the very foundation of how we understand gravitational physics and cosmic evolution. There are also debates about the Hubble constant tension. Webb's data, instead of solving the problem, seem to reinforce the discrepancy between different measurement methods. This has opened space for bolder hypotheses, such as the possibility that dark energy is dynamic, or that the laws of gravity need to be revised on cosmic scales. While some researchers call for caution, arguing that more data are needed before drawing drastic conclusions, others already see in Webb a sign that we are on the threshold of a new scientific revolution. These controversies should not be seen as failures, but as signs of the vitality of science. It is natural for new instruments to bring unexpected results, and with them, heated debates. It was so with Galileo when he pointed his telescope to the sky. It was so with the Hubble telescope when it revealed cosmic acceleration, and now it is so with James Webb. Controversy, far from being an obstacle, is the path that leads to deeper discoveries. In the end, consensus and controversy go hand in hand. Everyone recognizes Webb's greatness, but not everyone agrees on what its data mean. This dialectic is healthy and necessary because it forces the scientific community to refine its methods, question its theories, and perhaps prepare the ground for a new way of understanding the universe. James Webb, more than a telescope, has become a catalyst for debates that may redefine the boundaries of modern cosmology. The standard cosmological model, lambda CDM, has for decades been the most solid framework of cosmology. It combines Albert Einstein's general relativity with the concepts of cold dark matter and dark energy, and it has managed to explain everything from the cosmic microwave background to the formation of the cosmic web of galaxies. However, the discoveries of the James Webb Space Telescope have opened cracks that may require not only adjustments, but also new theories that go beyond the boundaries of this model. This is the point where cosmology begins to intertwine with fundamental physics, exploring territories that still have no answers. One of the most discussed hypotheses is that dark matter is not completely cold, as assumed by lambda CDM. If the particles that compose this substance are slightly lighter, or have properties that allow them to interact subtly with ordinary matter, galaxy formation could have been faster and more efficient, which would explain the early objects found by Webb. This scenario of a warm dark matter, or even non-interactive dark matter, is already being tested in simulations, and preliminary results show that it may better reproduce some of the telescope's most surprising data. Another frontier lies in dynamic dark energy. Lambda CDM treats dark energy as a cosmic constant, uniform and immutable, but some cosmologists suggest it may vary with time or with the density of the universe, functioning as a still unknown quantum field, sometimes called quintessence. If this hypothesis is confirmed, it would mean that the acceleration of cosmic expansion is not a fixed phenomenon, but an evolving process that may have been different in the past and could change in the future. Webb's refined measurements, by mapping expansion in earlier epochs, may provide the necessary clues to assess this possibility. There are also even more radical proposals related to modifications of the laws of gravity. Some physicists argue that dark matter itself may not exist, but rather that Einstein's equations deviate when applied on cosmic scales. Theories known as modified gravity, or MUND, attempt to explain the effects attributed to dark matter as the result of a new form of gravitation. Although these ideas still face difficulties in reproducing all phenomena, Webb has brought new data that force reconsideration of how universal our current equations really are. Another frontier is the connection with particle physics and the search for a unified theory. The early universe, revealed by Webb, is a natural laboratory for testing hypotheses about exotic particles such as axions, sterile neutrinos, or even stranger states of matter. If these particles really exist, they would have left traces in the formation of the first galaxies, traces that Webb may be beginning to reveal. This bridge between the infinitely large of cosmology and the infinitely small of particle physics is perhaps the most promising and challenging frontier of all. Finally, some theorists suggest that the very concept of the universe may need to be reconsidered. Ideas such as the multiverse, additional dimensions, and even the hypothesis that we live in a simulation have gained new momentum in the face of the tensions created by Webb. Although many of these proposals remain beyond immediate verification, they show that the frontier of physics is not only technical, but also philosophical. To what extent can our theories truly describe reality? James Webb, by revealing early supermassive black holes, giant galaxies at improbable times, and halos of dark matter larger than predicted, is pushing us beyond the comfort of lambda CDM. It is not about abandoning the model, but recognizing that it may be only a chapter, not the whole book. The new frontiers of physics demand intellectual courage to imagine alternatives and scientific rigor to test them. Webb shows us that the cosmos still holds mysteries that challenge even our best theories, and that the adventure of knowledge is far from over. The James Webb Space Telescope marked the beginning of a new era in astronomy, but it will not be the last chapter of this journey. Its success has opened the way for new missions to be planned, with the goal of going even further, exploring other frontiers and answering the very questions it has raised. If Hubble was the telescope that consolidated the standard cosmological model, and Webb is the one that is challenging it, the next instruments may be those that finally pave the way for a complete revolution in our understanding of the universe. One of the main projects under development is the Nancy Grace Roman Space Telescope, planned by the United States Space Agency. It will have a field of view 100 times larger than Hubble's and will specialize in studying dark energy and the large-scale structure of the cosmos. With it, scientists will be able to map millions of galaxies and measure precisely how the expansion of the universe has evolved over time. Roman will function as a natural complement to Webb. While Webb sees the deep detail of specific regions, Roman will have the panoramic vision capable of placing those details into a broader context. Another promising mission is Athena, planned by the European Space Agency to observe the universe in X-rays. It will have the sensitivity to investigate supermassive black holes, hot plasmas, and invisible structures around galaxies and clusters. Its role will be decisive in understanding the processes of accretion and feedback from black holes revealed by Webb. By observing the same cosmos in different wavelengths, the two telescopes will offer a complementary view of cosmic evolution. There is also the LISA, Laser Interferometer Space Antenna project, a gravitational wave detection mission to be launched by the European Space Agency in partnership with the United States Space Agency. This mission will open a new observational window, detecting vibrations in spacetime caused by the mergers of supermassive black holes, the very objects Webb has been observing in the young universe. The combination of deep infrared images and gravitational waves will be an unprecedented leap, allowing the study of the formation and evolution of black holes from their origins. Beyond these missions, the direct successor to Webb is already under discussion, the LUVOIR, Large UV Optical Infrared Surveyor, or similar concepts. This future telescope would have an even larger mirror, reaching 15 meters in diameter, and would be able to study exoplanet atmospheres in search of signs of life, as well as investigate the nature of dark matter and dark energy in greater depth. If Webb has shown that the universe is more complex than we thought, LUVOIR or another equivalent project may answer whether we are truly alone in the cosmos. The future of cosmic observation, however, is not limited to space. More powerful supercomputers, underground detectors for dark matter particles, and next-generation ground observatories, such as the extremely large telescope currently under construction in Chile, will join space telescopes to form a global network of investigation. This synergy between observation, simulation, and theory will be essential to tackle the tensions exposed by Webb. Ultimately, James Webb is not just an end, but a beginning. It inaugurated a chapter in which cosmology can no longer afford to ignore discrepancies. Its successors on Earth and in space will have the mission of transforming tensions into discoveries, doubts into solid theories, and questions into answers that will redefine humanity's place in the universe. The future of cosmic observation is, above all, the continuation of a journey that began when we first looked up at the sky and asked, where did we come from and where are we going? Webb brought us a little closer to those answers, but the true destination still lies beyond the horizon, waiting for the next eyes humanity will cast into the cosmos. We have reached the end of this long journey through the universe, revealed by the James Webb Space Telescope. We explored early black holes, quintets of galaxies, invisible halos of dark matter, and even the epoch when light first traveled freely through the cosmos. Each discovery reinforces that the universe is far more mysterious and fascinating than we imagined, and that science is only scratching the surface of this ocean of knowledge. If this content helped you dive into space and relax while learning, I kindly ask you to support the channel. Subscribe now, turn on the notification bell so you do not miss the next videos, and leave your like, because that helps YouTube recommend this content to more people who also love science. And now I want to hear from you. Where are you watching this video from? Write in the comments your city or region, because it is always amazing to see how far our community of universe enthusiasts is reaching. Thank you very much for staying with me until now. I wish you a wonderful night of rest, full of peaceful dreams inspired by the stars. See you in the next video, where we will continue together exploring the wonders of the cosmos.